So dear students, dear colleagues, welcome to this afternoon session. Let me check only if the whole commission is present. Professor Vanali, welcome. Professor Accorsi, welcome.
Thanks.
Professor Pompoli, welcome. And so, are you there, Gianni? Not yet? I don't know, Marcello, if you are trying to contact Professor Nicoletto. I can hear you. I don't know why.
Now you hear me? Can you hear me? Francesco, can you hear me?
Yes.
Now okay. Now I don't know. It was some of the settings of Teams. I think that Gianni is coming because he left the Consiglio di Dipartimento saying that he was coming to the session in MUNER. So I guess he's coming. Maybe I'll text him a message.
Okay. I sent him the link in case of issues. So while we wait for Professor Nicoletto, I would like to call and to verify that at least the first group of students is present. Eleonora Mazzoni.
Yes, I'm here.
Thank you. Angione Andrea.
Yes, I am.
Okay. Lorenzo Belletti.
Here I am.
Valerio Caliciotti. Valerio, are you there? Not yet. But we have time for his connection, so you are confident that he is going to join us. Well, you know that the event is broadcast in streaming on a YouTube channel. You should have received the link for your friends and parents and relatives, and obviously that means that we are recording such an event. So obviously, if you have any issues about that, please tell us, because this is a sort of acceptance of the streaming. Okay. Let me check if Gianni was able to join us.
Excuse me, I'm Valerio Caliciotti. Sorry for the late.
Okay, so welcome.
Thank you.
Thank you. Gianni, may you hear me?
Yes, I can hear you.
Sorry, thank you so much.
Sorry about it. I don't know why it had this problem. Okay, I can show myself.
Okay, so thank you so much. So we are ready to start, and so I invite all you to switch off your camera and microphone, and only the candidate and the person who speaks is authorized to switch on the camera. So as I told you, we are broadcasting the event in our YouTube channel. But the first speech is from Eleonora Mazzoni, so welcome. And
Yes.
I kindly ask to Professor Betocchi, who is the supervisor of Eleonora, a very short introduction to her. Sorry, Enrico, we cannot hear you.
Now?
Yes.
Okay. The thesis deals with finding a suitable optimization procedure for designing a sheet metal formed web of stiffening ribs to be applied as an underlying reinforcement to transversely loaded, otherwise static panels. The automotive front and rear hoods are typical applications for the proposed procedure. Also, similar structures are also found in chassis subframes. Basically, two methods are analyzed, both based on the optimization of a sandwich panel counterpart for the stiffened plate. Then, this optimization is followed by a partial redesign due to the different manufacturing constraints. I now yield the floor to the candidate.
Okay. I start the presentation.
Yes, please.
Okay. Can you see the presentation?
Yes, perfectly.
Okay. Good afternoon, everyone. Today I'm going to talk about the methods for the optimized design of sheet stiffening ribs. Engineering practice often highlights the necessity to improve the performance of a structure, reducing its mass, preserving adequate stiffness and resistance. And nowadays, optimization is the most powerful tool to minimize or maximize certain quantities as long as certain constraints are not violated. The aim of this thesis is to apply structural optimization, in particular shape and topology optimization, to find the optimal design for sheet metal form stiffening ribs. The idea is that of reproducing a sort of car hood consisting of an outer and an inner panel, but with a simpler shape, a simple sandwich structure whose upper panel will be the design variable of the optimization. So the stiffening principle, we want to start from a base panel, the aesthetic panel, so the outer panel of the hood, for example, and we want to stiffen this panel with a counter panel that will be placed at a certain height to increase the moment of inertia and therefore the bending stiffness. Two types of shear connections can be created. One adding a core in between the two panels, obtaining in this case a sandwich panel structure, or creating a rib and connecting it with the base panel with welds, for example, obtaining this omega-shaped sheet metal formed stiffening rib. As a first view, these two models are similar, equivalent, since both increase the moment of inertia and both can guarantee the shear connection. But the shear connection is of two types, distributed for the core case and perimeter for the stiffening rib case. And this shear connection must be checked to verify that they are equivalent. So for this thesis, the sandwich panel structure will be the starting configuration, and we will end up with the stiffening rib model. Starting with the shape-based optimization, so we have the base panel, our aesthetic panel that cannot be changed, and a counter panel. On this counter panel, the shape variables are created with hypermorph, a module of hypermesh, and these shape variables are moved to find the optimal solution for the optimization problem. In this case, in this way, the thickness of the core foam for this shape optimization is modified, so is increased or decreased. So we want to obtain a model where the thickness of the foam is minimum, close to 0, to create the shear connection, and it is maximum, so it reaches the upper bound to generate, to increase the bending stiffness. For the shape optimization, a extra low density foam with low shear strength and low elastic modulus has been used, since where shear connection is generated, the thickness is very small, so low shear modulus is not a problem. And further stiffening of the model is negligible, since we have a low elastic modulus. So the models used for this optimization is a quarter of the full model. So we have symmetry constraint applied on this side and on this side. Here we have the support, and here we have a distributed force applied in that positive direction. As first attempt, 18 shape variables have been created, and they will be moved by the solver to find the optimal design to minimize the compliance. A bilinear interpolation is employed to cover the whole domain of the structure. This optimization ends up with a local minimum with an alternation of junction and race zones that is not the optimal shape expected. So 6 shape variables have been tested to help the solver to converge to the optimal solution. And we can see from this picture that this is in line with the expected solution. We have a terminal shear connection in this side, where here, in correspondence of the force, we have an increase in Z. We can further stiffen this model, creating another shape in correspondence of this side, opposite to the symmetry constraint. And the solver returns this shape where we have a perimeter shear connection on the new created shape and on the support. From this table, we can see the performances of the models, and by means of ratios. The mass is the ratio, so mu is the ratio between the mass of the case study and the simple plate of aluminum, and we can see that the mass of the optimized models is almost the double of the starting model. Instead, in terms of stiffness, we use the 2 different ratios. Key, the stiffness ratio between the case study and the simple plate, and eta, the stiffness ratio between the case study and 2 panels at a distance of 20 millimeters. So this is the best case where the core is taken as infinite stiff, and this is the worst case. And we can notice that the 7 shapes model is the best in terms of stiffness. Switching to topology optimization, the aim is that of decrease the element density of the design variable to minimize the mass of the structure with a compliance constraint that must be the compliance of the 80/400 sandwich structure that is also shown here. The yellow part will be our design variable, that is an extension and a lateral expansion of the previous model. And now for the topology optimization, we will use a core that is 20 millimeter thick, and it is made of honeycomb. Here we have the support, and here we have the distributed force. So we expect an enlargement of this purple part that is non-design variable in correspondence of the force. And we can notice from the optimized sandwich panel that is what happened. So where is blue, we have no fractional density, and where is red, we have full fractional density. Now we want to redesign this shape with a stiffening rib for the lower panel. And this is the created redesign. These times the stiffness is 30% less than that of the shape sandwich panel, of the optimized panel. Now we can switch to a general sandwich panel structure. The upper panel will be the design variable, and we want to minimize the mass with a compliance constraint that is the square root of 2 of the base model compliance. The force is applied on this hole, and the other holes are supports. This is the optimized shape of the optimization, and the redesign using the stiffening rib is this model here on the right. This time, the stiffness increases by 8% with respect to the optimized panel, and that can be seen also from the Z displacement contour, where the minimum displacement is higher in this picture here, that is relative to the shape sandwich panel with respect to the stiffening rib model. But the mass increases by 21% with respect to the optimized one. So we tried to further reduce the mass, creating holes on the lateral surfaces of the rib. But attention must be paid to the distance between these holes, since a minimum distance must be preserved to guarantee at least the integrity of one fiber of material that can transmit shear from the upper to the lower panel. This new redesign has a stiffness that is 8% less than that of the optimized sandwich panel, and in terms of mass, it is 4% lighter than the first stiffening rib design. The last model studied has the force applied on a side in line with the 2 supports, and also in this case the upper panel is optimized and the mass is minimized with a compliance constraint. This is the shaped sandwich panel, so the topology optimized model, and this is the stiffening rib redesign. The stiffness in this case drops by about 38% with respect to the optimized sandwich panel. And we can see from the deformation that there is a problem in the shear connection generated by the stiffening rib. So we tried to increase the stiffness, introducing rods between the 2 lateral surfaces of the rib, and this time the stiffness is only 3% less than that of the topology optimized sandwich panel. The problem now is how to convert these rods in a manufacturable manner feasible by sheet metal forming. So first possibility is the creation of a notch in this region, but in this case the moment of inertia drops and the gain in shear connection is not so relevant, so important. So this is discarded, and the second possibility is the creation of a hole in correspondence of the upper surface of the rib connected to the lower panel. This time the stiffness increases by 20% with respect to the first stiffening rib design. And looking at the deformation, we can see that now the trend of the Z displacement is more similar to that of the topology optimized sandwich panel, even if the minimum displacement is still higher than this one. So we can conclude that shape optimization has been proved to be not efficient for the optimal design of stiffening ribs due to the problematic that we have the presence of many local minima in the optimization and many plateaux. This issue can be mitigated by a meditated choice of the shape functions that can be done only for simple structure, as done in our shape optimization case. Increasing the complexity of the structures, it becomes cumbersome to define the shape function. So we switch to another type of optimization, the topology optimization, that has given promising results, even if the models are still a test case, so simple cases. The problem is that the native distributed shear connection of the honeycomb core has to be reinterpreted in terms of perimetral or punctual shear connection manufactured by sheet metal forming. And this is not an easily resolvable problem. We tried some solutions, but for some cases it results to be okay. The stiffness of the optimized sandwich structure with the stiffening grip model. For other cases, it is more difficult to guarantee the equivalence of these two types of shear connection. Thank you for your attention.
Thank you so much for your presentation, for your starting presentation. I kindly ask to all the candidates to stay in the 12 minutes, please, because we have a very long afternoon to pass together. But anyway, we have time for one short question from the Commission. So just a curiosity from my side, you told us that you obtain interesting results at the end. So which are the future development that you think that can be realized for such kind of application?
So maybe we didn't try to apply this optimization to a real hood, but maybe a further study could be the application of this topology optimization to starting a real upper panel of a hood, and see if also in this case this topology optimization could be an efficient solution for the stiffening of a real car hood.
Thank you. I kindly ask you to close the sharing of your screen.
Okay.
So we can see you.
Yeah, okay.
Any other questions or curiosity from the Commission? If not, we can move to the next candidate. That is Andrea Angione. And we host the company supervisor. Chiara, are you there?
Yes, I'm there.
So thank you so much. I kindly ask you to introduce very shortly the next presentation.
Yes. So the candidate completed this thesis activity in Dallara Automobili during its internship. And just a few words, the aim of this work was to introduce a new experimental test in our research mechanical testing laboratory in order to that could be applied to several joints, in particular in order to evaluate an extremely important parameter for us, that is the G1C in the framework of the fracture mechanics scenario. The approach that Andrea and Dallara followed is original, and it has been applied to different configurations and materials. And now I kindly ask the candidate to present its work.
Thank you.
Okay. Here I am. I hope you can all see my screen.
Perfect, yes.
Okay. So in the next few minutes, I'm going to present my master thesis work that, as my tutor introduced, is the result of the internship activity performed in Dallara Automobili. The main goal of the work was to get an accurate procedure to measure the fracture toughness in mode 1, that is called G1C, for carbon fiber reinforced polymers. And also another goal was the validation of the implementation of direct image correlation technique into the experimental procedure to get this property. To get to this result, the crack propagation during the test was monitored and recorded throughout the whole test. And the crack length measures were correlated with load and displacement values coming from an electromechanical machine. Also, a possible automation of the post-processing procedure was attempted during the activity. As a brief introduction, carbon fiber reinforced polymers belong to the category of composite materials. They are made of a polymeric resin and carbon fibers as a reinforcement. Also, additional components may be found in this type of materials. The most peculiar properties of these composites are for sure their anisotropy, which means that their mechanical properties strongly vary depending on the direction of measurement. And they are particularly attractive for the automotive sector and for motorsport for their high stiffness over weight and strength over weight ratios. In particular, they have become a standard material in motorsport since their lightweighting potential is used to gain a competitive advantage. They are widely used also in automotive, but nowadays only in those sectors in which cost is not a major material selection factor. Usually structural components made in carbon fiber composites come in a form of a laminate, and they are manufactured starting from prepregs that are sheets of woven fibers pre-impregnated with the resin. Several layers of prepregs are stacked onto a proper mold that has the shape of the final components, and then the whole assembly undergoes the process of bag molding, which means that the component is cured into an autoclave, where a combination of vacuum, high pressure, and high temperature is maintained for a predetermined amount of time. A possible failure of these components is hence the separation of the layers one from the other, that is called delamination. So how it is possible to predict this failure? Usually the parameter that is used is called interlaminar fracture toughness, that is associated to critical energy release rate, that is the energy consumed by the delamination front to advance through a unit area. So it is measured in joule over square meter. There are three possible modes in which this phenomenon may happen that are shown in figure. And in particular, for the first two, standard procedures are available to test the properties of the material. In particular, for mode 1, the procedure is the double cantilever beam test, that is the focus of this work. And there is also end-notched flexural test for mode 2 fracture toughness. This is a brief overview of the experimental equipment and of the specimen that we used throughout the activity. The equipment consists of an electromechanical testing machine equipped with a position transducer and 2 load cells. And also the direct image correlation system is shown on the bottom left of the slide. Geometry and dimensions of the specimen were taken from an ASTM standard that is usually applied to measure fracture toughness in mode 1. And the technical drawing of the specimen can be seen on the right side of the slide. We also compared the 4 calculation methods proposed by the regulation to observe possible differences among them. This is an example of the typical acquisition from the DIC system. As we can see, the 2 load signals are acquired together with the cross-set displacement that is measured directly on the specimen fixture. In the table, you can see the 4 different materials that we tested. They have different combinations of fibers and resin. We chose these 4 materials because we expected them to have quite different values of interlaminar fracture toughness. So we wanted to assess the performance of the experimental setup throughout the whole scale of possible values. This is an example of the raw data coming from the experiment. That is basically a load versus displacement curve acquired by the 2 different load cells. We can clearly distinguish the 4 phases of the test that are the preloading that is needed to make the delamination front propagate from the initial position that is given by the insert. Then we have a first unloading, the loading phase, that is the phase that is used to get the property of fracture toughness for the material, and then the final unloading to go on with the next tests. After the application of the 4 methods proposed by the regulation, we get the value of fracture toughness in mode 1, that is V1. These plots are the resistant curves coming from the first material, so from set 1. These plots basically represent the value of fracture toughness versus the cross-set displacement. As we can see, for all the specimens, the only methods that gives an overestimation of fracture toughness is modified beam theory, that is the blue curves, while the other methods provide very similar results compared one to each other. These are the numerical values averaged on the whole set of specimens. And as a reference, we took the datasheet of the materials. And as we can see, for all the calculation procedures, excluding the first one, we got values that are into the correct range with respect to the datasheet. This is also a brief description on our attempt to automate the post-processing procedure. Basically, we draw some vertical lines virtually on the DIC software, and we monitor their variation of vertical length to associate it to a propagation of the crack in correspondence to that line. As we can see from the plot and from the numerical values, the correlation was pretty good, but unfortunately, this happened only for this first set of material, because this correlation, we found it to be strongly material dependent. So we decided to go on with the visual observation of the crack propagation. On the other hand, we managed to simplify the preparation of the specimen and to shorten the test time. These are the resistant curves of the second material. As we can see, the behavior of the calculation method is the same with respect to the previous case. And these are the numerical values. In this case, we didn't have available the datasheet of the same materials that we tested. So we took as a reference a similar material that has the same resin, but it has a different resin percentage. And most importantly, a different density of the dry sheet of fibers. In this case, we found an experimental value that is pretty much double with respect to the reference, but it is a coherent value because fracture toughness is expected to grow with the density of the dry fiber sheet, and our material had a density that was 4 times with respect to the one of the reference. This is the third set of materials. The behavior of the calculation method is confirmed once again, and we obtained the highest value among all the tested materials. In fact, the resin used in these materials is a toughened resin, which means that it is purposely designed to increase interlaminar fracture toughness. Unfortunately, we didn't have the datasheet value available for this material because it comes from a different producer with respect to the other materials. This is the last set that we tested. Once again, the calculation methods show the same behavior. And these are the numerical values that we obtained averaging on the 4 specimens. As a reference value, we had in this case the datasheet of this material. As we can see, we obtained a slight overestimation of the fracture toughness value, but after a confrontation with the producer, we came to know that they use a different method to post-process the experimental data, so probably the difference is due to this different calculation method. Anyways, the values that we obtained are pretty much similar to the reference one. So to conclude, the experimental procedure was validated with a visual observation of the crack length. And for what regards the calculation methods, they are all considered to be valid, except modified beam theory, that is the first one that is shown to overestimate fracture toughness value. We obtained the possibility to record the experiment, to post-process the data in a second moment with respect to the test, and we also managed to simplify a lot throughout the activity the preparation of the specimen. As future developments, further analysis on the automation procedure may be attempted, in particular analyzing the material dependence, and also an evaluation of a thickness reduction of the specimen may be studied, since the ones that we used were quite thick. With thinner specimens, also top surface analysis approach may be attempted. That consists in observing the specimen from the top side instead than on the lateral side, as we did. And also the same procedure may be applied to hybrid joints, and also to N-notched flexural test to measure mode 2 interlaminar fracture toughness. And that's it. Thanks for your attention.
Thank you so much. Any question or curiosities from the Commission?
Excuse me. Can I ask you a question? Very short question. I'm Gianni Nicoletto.
Yes, thank you, Gianni.
Okay. I would like to ask you, these experiments on fracture mechanics of these bonded joint or interface cracks, are they supposed to feed some model, final element model, or any, design-oriented application, or is essentially a material characterization work?
Let's say it has both the purposes. Indeed, into the company, a correlation with FEM modeling is undergoing, starting from the experiments that we did during my internship. And of course, the final goal is to have an accurate data for fracture toughness to be inserted into finite element analysis for design purposes, as you said.
Okay.
Thank you.
I have another curiosity. Have you conducted experimental tests with quasi-static load, or even dynamic frequency tests? And in this case, what changes in your analysis in case of dynamics loads?
In the analysis that we conducted, the load is quasi-static, and the loading speed is prescribed by the regulation. Of course, the dynamic loading is of great interest, but we limited to static load during this activity.
Okay.
Thank you. Thank you, Andrea. Thank you to the Commission. And so I ask to the next candidate to switch on the camera and to share the screen. So welcome, Lorenzo. And I guess that there is your supervisor, but maybe also the company supervisor, or?
I guess that the company supervisor didn't join us, but I don't know. Probably Lorenzo knows better.
Yeah, he had some problem with the Teams,
okay.
with the connection.
Okay, so no problem. So
I can speak on behalf of him, of course.
Yes, thank you, Riccardo. If you want to introduce the candidate.
Okay, yeah, thank you, Francesco. Lorenzo carried out its thesis project within and along with this period spent in an internship in Lamborghini, and the rationale and the motivation of this project was about to try to get value from the available data provided by the let's say user interface available in company, and particularly he tried to integrate with data collection provided by SAP and collect some data dealing with the material flow of components used to serve and to feed the line. Given this, the project conducted by Lorenzo was about the manipulation of such data through some interfaces that he developed, and with the purpose to to carry it out and leading and supporting decision making on material flow, particularly in the light of the design of the best strategy to serve and to feed the line. But I don't want to steal time to Lorenzo, so please take the stage and we will listen to you.
Thanks to the introduction. I'm Lorenzo Belletti, and good afternoon to everyone. Can you see my screen?
Yes, we can.
Okay, perfect. I will present my thesis done in the Lamborghini company entitled Method and Interfaces to Aid Material Flow Analysis in an Automotive Production Plan, Automobile Lamborghini Case Study. Let's start with the agenda. First of all, I will introduce the case study. Then I will speak about the Lamborghini plan layout and the material flows. Then we'll go into detail about the data collection and the Visual Basic analysis. Later, we will see a virtual model built on the plan simulation software. And finally, we will get some conclusions. The thesis, as I said, it was done inside the Lamborghini. It was founded in 1963 by Ferruccio Lamborghini. In 1998, Audi buys the company and invests a lot of money on it. And nowadays, in 2021, Lamborghini sells three of the most famous super sport car in the world: Aventador, Huracan, and Urus. The aim of the thesis is to define method to support the material flow analysis, with a particular focus on the trade-off between the shuttle frequency and the size of the exchanges area. In order to do that, are used some tools like Visual Basic script and a virtual model built on the plan simulation software. Here on the top of the slide, there is a schematic that represents the material flow inside the Lamborghini. Of course, the first actors are the suppliers that are producing the goods. Then they are moved via truck to the warehouses inside the Lamborghini plant. Then, using Plattenwagens, that I will show you later what they are, the materials are moved to the handling area. Then they go into the supermarket, and then finally they go into the assembly line. In this thesis project, the analysis will be focused on the step from the warehouses to the handling area. Here we have the layout of the company. In red are highlighted the production building. On the top we have the SSC, that means a super sport car, and this is the building where there are situated the assembly line for the Huracan and Aventador. Here we have the Urus assembly line, and below the building for the paint shop. In purple, there were highlighted the handling area. In yellow, the logistic buildings. We have the TLC, Temporary Logistics Center, FLC, Final Logistics Center, that are the two warehouses, and then the body white park. In green, there is the CFK, that is the building where all the carbon fiber parts are produced inside the Lamborghini. Talking about the material flows, in light blue, we have the flow to SSG in order to feed the line of Aventador and Huracan. Then in yellow, we have the one related to the Urus. In green, the one related for the CFK, the carbon fibers production. And in the white related to the paint shop. In Lamborghini, what we are moving containers. We have four main types of containers. On the left, we have the GLTs, that are the biggest container, and they can be moved only with forklift. They can be standard if they are shared within all the Volkswagen Group plants, or they are special if they are directly developed by Lamborghini for some special part numbers. Instead, on the right, we have the KLTs, that are the smallest container, and they can be moved by hand. Of course, also for them, we have the same distinction between a standard and the specials. We are moving them using this Plattenwagen, that are these wagons attached to a car. So the analysis will be focused on the material flow related to the Plattenwagen, so the flow from the warehouse to the handling area. Here, from a data extraction performed on SAP and then an analysis performed on Excel, using the hypothesis that one GLT is equal to 12 KLTs in average, we measure the material flow size. Of course, as you can see, the Urus is the biggest flow in terms of containers per day. So the analysis, the follow analysis will be developed on about this flow. Is important to set up, however, the analysis, the methodology can be applied also to the other flows. Going into more detail about the analysis, the first step was to collect the data from SAP, the ERP management system. There were collected all the material movements from the warehouses to the production lines for the month of July 2020. The most useful data are the material code, the quantity, and the material code date and time. The second step was performed on Excel, and at this big table on Excel, there were added some useful information like the container type, the container's dimensions, so all the useful information related to the containers that are fundamental for the next steps. As a third step, it was develop a Visual Basic script that for each row of the file, that is a material call, it assign it a Plattenwagen trip unique code. So it means that that line, it was moved on that Plattenwagen trip that is unique in the month. From in this way, using the pivot table, we can have for each Plattenwagen trip that is highlighted in red, the distinction between GLT and KLTs, so the containers type, the base dimension here in green, the number of the containers moved for that particular trip. Here in purple are calculated the sum of the area and the volume of the containers moved. In order to perform a better analysis, it was developed another Visual Basic script in order to calculate the real area occupied on the ground by the containers, considering the fact that some containers can be moved stacked as two, so one on top of the other. As we can see, here there are two containers with the same base dimension, and the actual area is just the half of the one calculated by the pivot. From there, we can easily calculate also the filling efficiency for each Plattenwagen trip. Then we represented the results using these charts. On the x-axis, we have all the Plattenwagen trips. In the y-axis, we have all the saturations. In blue are reported the actual saturation, and in yellow the average. On the left, we have the one for the make-to-order, instead on the right for the make-to-stock materials. Then, moving on, we evaluate some to-be scenario. It was the aim was to find a trade-off between the shuttle frequency and the base size. Of course, if we increase the shuttle frequency, we need less space in the handling area. It's important to underline that the presented analysis methodology is parametric, so it can be applied also for different frequency in order to find the optimal trade-off. In the first scenario presented, we increased the Plattenwagen frequency from an as-is scenario of 23 minutes to a to-be scenario of 15 minutes. So it means that every 15 minutes in this scenario, we have a Plattenwagen trip. The advantage is that we require less space in the handling area. However, on the other hand, we have the drawbacks that we are decreasing the average Plattenwagen saturation, and also we are traveling more distance. Instead, on the scenario 2, we are decreasing the Plattenwagen frequency up to 30 minutes. Of course, we have the opposite advantages and drawbacks. Moreover, here we have also the risk of having some trips with a saturation higher than 1. Parallel to this analysis, it was also implemented a virtual model on the plant simulation software in order to analyze the material flows. It was done with the help of a Siemens consultant. The input data requested by the software are the layout, the material requested by the lines, the containers and trailers data, and the flows. By simulating it in the software, the results that can be obtained are the number of delays, the Plattenwagen saturation, the base saturation, and also an estimation of the handling area sizing. To conclude, here are reported the quantitative evaluation of the to-be scenario. As we can see in the first scenario, where we are increasing the Plattenwagen frequency, we can save up to 25 square meters in the handling area. However, the average saturation for the Plattenwagen trips is decreasing, and also we are traveling more distance. On the opposite, in the second scenario, where we are decreasing the Plattenwagen frequency, we need more space in the handling area, and also we have some trips with a saturation higher than 1. However, we have a average filling efficiency that is higher, and also we are traveling less distance. To conclude, the aim of the thesis was to define some methodologies to help and support the material flow analysis, with a particular focus on the trade-off between the Plattenwagen trip frequency and the space needed in the handling area. Another aim was to develop a virtual model on the software plant simulation. As future improvement, the Excel analysis can be extended also to the other material flows, like the Huracan and Aventador one. And also the model built on the plant simulation, it can be refined and fine-tuned in order to correlate it better with the reality. Thanks for the attention to everyone.
Thank you so much for your presentation. Well, I have just a curiosity. You told us that you realize a parametric method in order to approach the problem of the optimization. Do you plan to use any algorithm for the optimization within your model?
It can be done because yeah, if you set a number of inputs, you can try to find the optimal one. But the optimal, it depends about a lot of physical constraints that we have, because here we are considering just the logistic. However, in a company, there are a lot of other departments and physical constraints. Like you have to also give space to the production or to quality. So the optimal is just not for the logistic, but is to find the optimal. It has to be done a more general analysis in order to find the best solution.
Thank you so much. And what about the intersection between the material flow of this model and the other material flow that you have in plan to analyze in the future? Any intersection, any problem of compatibility between the materials flows? Or are they independent, let me say?
Yeah, I think they are quite independent. Like all the material flow, you can change one without touching the other if it's necessary. Otherwise, you can try to change both, all the material flow, in order to find the best way if you have to modify just one.
Okay, thank you. Any other question from the Commission?
Sorry.
Yes, please.
Thank you, Lorenzo, for your presentation. I was wondering if you can share with the Commission about other potential indicators of performance that can be collected or gathered from an analysis such like the one that you carried out.
Yeah, there are a lot of potential. Like it
so,
can be.
Yeah.
If you want to go on, sorry.
No, sorry. It was just if you so you collect data, you grab data, you manipulate it through your interfaces. Are any other metrics of performance or indicators that you can calculate and can lead other potential decision making?
Yeah, of course, there are a lot of plenty of information that you can collect from a database of data. The important is the collection of the database and the fact that the data are reliable. Then, depending on the purpose of the analysis that you want to obtain, you can modify the data in order to get what you want to achieve, like to find the perfect number of Plattenwagens that I didn't touch this point, but it can be done to find the optimal number of resources.
Or either, for example, to count the labor time spent in traveling or moving or handling material. Okay, thanks.
Thank you so much. So it's time to move to the next candidate, Valerio Caliciotti. So please join us. I cannot hear you, so you have to switch on your microphone.
Good afternoon. I'm
welcome. I don't know if the company supervisor is present, is attending our meeting.
Yes, I'm here. Can you hear me?
Yes, perfectly. Yes. So please, Andrea, if you want to introduce Valerio.
Yes. Good afternoon to everybody. I'm Andrea Nicolazzo, the supervisor of Valerio. He worked on his thesis about are new components that can be used in our suspension. And I would like to focus on the fact that this component, this system is very new for Dallara. So it's the first time that we study and develop this system. Thanks to the Valerio thesis, the first result are very encouraging. So we're really looking forward to keep studying the system, and hopefully we will introduce this system, this component in the following in the next car that we are going to design in the near future.
Thank you. So please, Valerio, you can share your screen and your presentation.
Now should 1 second. Okay. Now you should see also my laser. Okay. Can you see my laser?
Visible.
Okay. Good evening, I'm Valerio Galiciotti and I'm going to present my master thesis about the design of an asymmetric anti-roll bar system for a high performance Formula car. Before starting, I want to thank my advisor, Professor Gianni Nicoletto, and my co-advisor, Dr. Andrea Nicolazzo, for their precious help for this master thesis that I've carried out during my internship in the Dallara Design Office. Okay. All of us European people are used to watching races in which the tracks have both right and left-hand corners, and the cars are perfectly symmetric. But there is another vision of the motorsport, the American vision, in which sometimes the tracks have only left-hand turns, and this strange morphology lead the production of the car in this quite strange view, so heavily asymmetric. Here we can observe half of the front suspension of the Dallara car that we have analyzed, and in the right picture a detailed view of the anti-roll bar is presented. It consists in several parts, but the key elements for this thesis are the droplings. The droplings are elements that work only in tension or compression, and in this car, while we are turning to the right, the pink dropling is in tension while the yellow one is in compression, and in the left-hand corners the opposite happens. The aim of this thesis is obtaining an anti-roll bar system that has a symmetric layout, but with an asymmetric stiffness in order to maximize the car performances in some particular tracks. For example, the tracks in which the most important fast corners are the left-hand corners and the most important slow corners are the right-hand corners. Asymmetric stiffness because we have to match two different needs. The aerodynamics want to have a fixed position of the chassis of the car with respect to the ground in order to maximize the ground effect, in particular at the high speed. So in the fast corners we must have a stiff anti-roll bar to minimize the roll angle. From the vehicle dynamics point of view, we have the opposite need. We want to maximize the lateral grip in the apex of the corner and the acceleration out of the corner. So we have to maximize the contact patch in order to maximize the performance in this situation. This acquires more and more importance in the low speed corners because the limiting factor is the grip. So with this solution we can avoid this problem. Without knowing which could be a decent level of asymmetry, we want to cover the entire range of stiffness of the actual system that, as we can see in the upper picture, goes from its maximum to its 12%.
the loads that the drop link have to sustain in the jump over curb maneuver that is standard for Dallara are reported in the lower picture, and we can note that those loads are luckily quite constant. The final idea is to create an elastic drop link that engages the spring only while it is compressed, in order to have an elastic drop link in compression and a rigid or almost rigid one in tension. To cover the huge needed range of stiffness of this drop link, we have selected the use of Belleville springs because they are economic, lightweight, but most of all they can create incredible modular spring pack. And this is the final design, so an assembly composed by 8 parts made from 4 different materials, 2 types of steel, the aerial and also the bronze for the central part. After the design and the production phases, I had the fortune to start the test session. The first tests were performed at the static rig. There we have tested the strength and the stiffness of the drop link. To run this test, we have used 2 vertical fixtures to place and hold all the hardware that we have used, an hydraulic jack to force the drop link both in tension and in compression, a load cell to measure this force, and also a laser displacement sensor in order to understand which is the deformation, the elastic deformation of the drop link. And we used several types of Belleville pack, and here there are the results of the compression test in the lowest and the highest stiffness configuration, and both of them clearly show a hysteretic behavior, but this is due to the friction between the Belleville. This is confirmed by the fact that the average of the values are quite similar to the predicted values. After the static rig, we have continued the tests at the poster rig. This is a particular rig characterized by the presence of 4 hydraulic actuators, 1 for each car wheel, and the use of the real car mock-up. So this is a mock-up in full scale. With this machine, we can individually excite each wheel and each actuator has a load cell, a potentiometer, and an accelerometer. In order to improve the quality of the test and then its analysis, we have added 2 potentiometer on the dampers. In this way we can measure the displacement, so the deformation of the dampers, and also a load cell in order to measure the load that passes through the drop link. 2 types of tests were conducted, the so-called constant frequency test and the work test. In the first test, so the constant frequency, we have simulated the heave, so the vertical displacement of the chassis, in order to check that the anti-roll bar doesn't work in those situations. And the work test has the aim to measure the car in roll maneuver. Here we can see the plots, the plotted results of the post-week test session. These results are compared with the expected values, and here in the left figure we can see that the asymmetry is quite low, because the asymmetry of the anti-roll bar is reduced by all the other symmetric components, such as the corner spring and the tires, because this is a roll stiffness characterization at the pads, so at the wheel. While in the right picture we can see the characterization in the ends, at the end of the anti-roll bar, and here the asymmetricity, the asymmetric is quite evident. As future developments, we want to perform fatigue tests in order to understand which could be the fatigue life of this assembly. The test at the driving simulator must be done, because we must include a human in the loop. We need its feedback, and then as conclusion, the test on track. This was my last slide. Thank you for the attention.
Thank you, Valerio, for the presentation and for sharing with us such an interesting results. Well, I have a curiosity or a question for you. So, did you develop any variant with respect to the design that you described as? Can you tell us something about that?
Yes, for sure. This drop link can mount several pegs of Belleville, so its stiffness can be tuned. And then we have started with other typology of drop link. For example, composite drop link, in which we used the asymmetric behavior of the carbon fiber. And also we wanted to create a particular support for those drop link in order to realize this asymmetry in roll stiffness that we want to achieve.
Thank you. Any other question from the Commission? No, so your presentation was clear enough. And that's a good point. So the next candidate is Riccardo Calzoni. And I see that the company supervisor is present here in our meeting.
Yes, it should be present.
Yes. Is Carlo Berni? So are you there? We cannot hear you. So I propose to, it's entering again, so maybe. Okay, Carlo, are you there? Can you hear us?
Yes, I'm in. Sorry for the delay, and good afternoon, everyone. So, a short introduction for Riccardo. Riccardo was inserted in our team in logistics series for Automobile Lamborghini starting from June 2020, right after the, let's say, first lockdown that every one of you for sure remember. This was really a quite tough period for the reopening of the activities in Lamborghini, and he had the opportunity to see first the development of some KPIs, and then to take part in the real core activities of the material planning for the logistics series process of the procurement of the material. It was really a tough period for the supply chain, and he took the opportunity, this new opportunity, to develop a tool that was a tool for notification of the delays to our suppliers. And this was really helping us to improve our activities and be really effective and more efficient during our daily job. So I want to really thank you, Riccardo, for the job done for our department and for the company itself. Thank you very much, and please go on.
Thank you, Carlo. Okay. So you should see my presentation now.
Yeah, perfectly.
Okay, so good afternoon to all. Today I present you my thesis work entitled Serious Material Planning during SARS-CoV-2 Pandemic Spread, Automobile Lamborghini Case Study. First of all, I would like to thank Professor Regattieri and all the LP24 team for the great support they gave me during this incredible experience. Now you can see the agenda of the discussion, which will deal with the following topics: the objectives of the internship project on which the thesis was developed, an overview of the serious logistics department with particular reference to the planning team whose activities I supported during this period, the impacts that the spread of SARS-CoV-2 is having on material planning work, and finally a solution that has been proposed and developed to improve the management of the so-called expired orders. As mentioned, the internship was carried out in Serious Logistics Department in Automobile Lamborghini, where I supported the material planning tasks for a customer's car. Therefore, the targets and activities that are up to the team in the daily business will be shown. This project lasted from June 2020 to February 2021 and was strongly characterized by the second and third wave of COVID-19 spread. Hence, the impacts generated by this situation of strong global instability on the entire supply chain will be discussed, inferring on the planning activity. Consequently, to counter these criticalities, it was developed a tool using a Visual Basic application that would allow to improve the management of delays by suppliers. The Serious Logistics is located within the Automobili Lamborghini industrial area and completes the organization of the logistics department together with program planning, operation logistics, and pre-serious logistics offices. It is divided into 4 main areas that are material planning, supplier management, stock management, and transport. Each group works synergistically with the others in order to guarantee the stability and continuity of the operations in all production and assembly lines. There are approximately 900 different locations from which the material arrives in Automobili Lamborghini to assemble customers' cars. If even just one of these components was missing, the car would not be producible, or at least it would be incomplete. So the material planning team has the goal to ensure the business continuity by guaranteeing the arrival of the right part in the right place within the right time and in the right quantity. Every day we therefore follow the flow of each component for which we are responsible on its journey from the supplier's production plant to the assembly line. The planning process is based on orders that are sent to suppliers by the EDI vendor program daily or weekly according to the material requirement planning. Stock levels and daily coverages are constantly monitored to prevent emergencies or complications that can lead to an interruption of the production activities. There are basically 2 types of material managed by planners: the make-to-stock materials that are not associated to a single car order and can be used on different cars depending on their configuration. We check them through the understock that is schematically represented here. In this case, we monitor the single material code by following the ascending order by days of coverage. The traffic light on the left is the first signal that allows us to identify possible criticalities. In fact, a yellow or a red traffic light indicates that the stock level may not be sufficient to cover daily needs. On the other hand, we have made-to-order materials that are associated to a single car order due to their high level of variance and therefore are unique. In this case, the monitoring has a different structure compared to the previous one. Planners rely on the order progress report, also called WIP, that allows you to monitor the material flow for GIS suppliers corresponding to every vehicle order. So the table presents a multi-matrix structure in which the status of each supplier for that specific car is highlighted. Material planning is based on the trade-off between cost and service level. The number one goal for sure is to have no missing parts, keeping as stable as possible the service level towards the production line. On the other hand, we try to reduce the warehouse space occupation, respecting the predetermined stock level and the working capital targets, avoiding costs for extra transport. The pandemic faced in the last year was certainly unpredictable. We all suffered the profound disruption triggered by this new reality. The emergency experienced could and should, however, become an opportunity for a breath of change, especially for production activity. To analyze the impacts on the material planning, we will go through three main steps that are the complete lockdown phase, the production restart, and the supply chain disruption risk. On 11th March 2020, the stop of the production lines was officially announced in Automobili Lamborghini starting from March 13th. The shutdown activities and definition was therefore immediate and therefore the cancellation of all shipments of material to the plant. Subsequently, it was important to define the stock coverage present both in Lamborghini warehouse and also at the suppliers. The succession of closures and later reopening of the various plants guided the path that led to the reestablishment of the supply chain. In order to ensure a resumption of the production lines without any kind of interruption, daily meetings were scheduled to monitor all the supply chain. The restart of luxury car manufacturers was necessarily subject to the decision taken by the mass-produced car makers. Therefore, the objective was to establish a restart date for the Audi Group plants that could guarantee satisfactory output in order to find a suitable trade-off. Without the guarantee that the market demand was such as to allow a restart, it was indeed impossible to prepare the offer for exclusive products. Although for Lamborghini the demand has not dropped down, it was unthinkable to guarantee an immediate recovery at full capacity, so it was decided to follow an adequate ramp-up phase, while maintaining the desired stability. With the arrival of autumn, the new outbreaks that raged around Europe created once again many difficulties to suppliers' plant. The limited resources at the production area were not always able to generate the outputs required by the program order, triggering delays in delivery and increasing the possible criticalities. So this project arises from the emergence of this new problem. In serious logistics, every planner is responsible for a number of material code that can vary from 500 to 1000. So the check could be extremely burdensome. In fact, the actual control of delays is done through a daily check performed with the ERP SAP software and an Excel file that contains all the active purchase order. To better manage this flow of information and increase the efficiency of this kind of operation, we thought to develop a notification tool for automatically sending the expired orders to the suppliers. The procedure has been written in Visual Basic application in order to combine the most used application by the team that are precisely ERP SAP, Microsoft Excel, and Outlook. Thanks to this tool, we moved from a manual control to an automatic process that starts from the active purchase orders present in the management software that are exported daily in Excel. Then, filtering by each MRP initial, it recognizes the expired orders and provides the planner a draft email in which are present the email address of the supplier, an Excel file attachment that resumes the backlog, and a preset text message in the desired language. Here you can see an example of the three systems that are involved, so SAP software, the Excel file obtained, and the draft email. The results are in target with the requests. In fact, after a trial period, we obtained a reliability increase in the expired orders monitoring, having removed the transcription error. The time spent to perform this activity is more than half with respect to previous condition. The control improved a lot because we can now simultaneously check all the purchase order at the same time and not singularly. And then, thanks to a specific API that analyzes the supplier's performance in terms of delays and the survey proposed in case of COVID-19 occurrence in the supplier's plant, we have been able to react promptly to many criticalities. Lastly, it's worth to mention that the economic aspect of this project, since no investments were needed, as the software used were already available. I conclude by saying that this global pandemic has brought out the need for change and adaptation even to off-standard situation that no one could ever predict. But if seized, they can lead to new challenges and opportunities. Thank you for the attention.
Thank you so much for your presentation. Any question from the Commission?
Yeah, I have one.
Thank you, Riccardo.
Thank you, Riccardo, too, for your presentation. I was wondering if you can, notwithstanding with the constraint of course, of company about the management and planning over their own manufacturing plan or schedule, could you give some, could you cite some model or some approaches that can be used to deal with uncertainty with the purpose of a better or more resilient manufacturing planning?
Okay, for sure, for us, it is important to try to predict the emergencies that can arise from the suppliers. For sure, every day we check, for example, also the COVID-19 spread in every country for which we have, for example, suppliers' plans for which we are responsible, and we try always to keep in contact with the logistic references that we have, because in this kind of situation, the communication becomes a very helpful in order to prevent this kind of criticalities.
Thank you. Thank you again for the presentation. Well, the next candidate is Paolo Costi, and I guess that is introduced by Cesare Stocchi.
Yeah, should be here.
Dallara. Okay.
Good afternoon. In Dallara, we have developed a method to study car components and especially bodywork when subjected to a history of vibrations or accelerations combined with aero loads with changes with the car velocity. So it's a FE simulation of a track lap replay when you can see instant by instant what's happening in the structure. But this method still needed a complete scientific validation, needed some improvements on some topics, and required quite a bit of human intervention and iteration to be worked. So we asked Paolo to validate it completely, improve the method on several aspects, and automate it as much as possible.
So, good morning, everybody. I'm going to talk about method development for an automatic model dynamics analysis of car components. Thanks to the tutors which helped me, which are Professor Pirondi and Professor Stocchi, and thanks to Dallara, which provided the 3D models and the data necessary for the development of the work. Which problem are we talking about? We are talking about problems of vibrations in race cars. As can be seen in this small video, the side mirror of the car is shaking considerably. This is a problem that can happen on many race cars. This could cause both safety issues due to the lack of visibility which can occur in this case, but also can lead to structural problems. In particular, breaking of vibrating elements, which can be, for example, side mirrors or weak aerodynamic appendices. So the problem is in the end structured like this. Starting from the track data telemetry, so the data coming and registered on the track, history loads are then computed. These loads are introduced into a finite element model, which allows for the analysis, so structural analysis of many components. In particular, during this work, the side mirror, high performance side mirror has been tested. The model is built like this. So there is a stiffness matrix, which is represented as the stylized shape of the monocoque in blue and the stylized shape of the roll structures in red. Then there is the red dot, which represents the positioning of the accelerometers inside the car. So it is just, let's say, an approximation. But in this place, constraints will be put inside the model to reproduce in the most correct way what happens on the track. Then there is the presence of history and field output, which are two kinds of results that can be selected inside the model. History, as the word says, allows for a monitoring of a parameter over several time steps, while field, let's say, is a screenshot of what happens in a single time step. So the solver is Abacus and is using model dynamics. Model dynamics is a simulation, linear and transient, so it's over time, let's say, where history loading are accounted for. Which are the main sources of loading? They are starting from the main one, which is the acceleration. So lateral, vertical, and longitudinal acceleration are inserted in the model, and they can generate strong structural effects. But there are also aerodynamic, which is moduled on the speed of the car over the track. So the force is changing during the simulation. And then there is the gravity, which is constant and proportional to the mass. As can be seen in this slide, I hope it works. There are a multitude of stress states which occur during the track lap. It is impossible for let's say a human to completely analyze all of them. So it is necessary to approximate and to create a method to analyze scientifically the problem. What is currently done in Dallara is the use of the so-called iterative method. In this case, there is the want to identify the most stressed instance on the track, all over the track. This requires iteration and the use of engineer experience. This iteration and the fact that the human intervention is required generates lack of precision, but also unrepeatability of the results. So a new kind of simulation, a new method is necessary to study the problem in, let's say, in a repeatable way, in a scientific way. So the main constraints are for sure the compatibility with what currently used, so model dynamic, but also the automation level is high automation level is necessary to prevent as much as possible the human error, let's say. Then there are other constraints like the calculation time, which are for sure important. The first method developed has been Abacus subroutines. So this method requires the use of a particular tool, which is available in Abacus. In particular, this tool allows for the communication of the engineer with the solver while the calculation is running, and not just once the calculation is ended. In particular, the use of the URD-FIL subroutine allows for the reading of a particular result file, which displays the results in a condensed way, so a more efficient and condensed way during the simulation. This allows for an overwriting of the simulation time step after time step, generating a very efficient algorithm. But in the end, this method showed unacceptable performances due to long simulation times. And a second method has been developed. It's called history analysis, because it requires the use of one heavy simulation which studies all the track, and all the elements are put in history output. So there is a huge amount of data to be analyzed. In this case, the need of automation, so the need of automatic post-processing was necessary. Otherwise, it is impossible to study such an amount of data. But again, the result analysis, the automatic result analysis, was not satisfying from the performances point of view, as we will see later. But this method is quite easy and customizable, so it can be maybe used in if future developments in softwares are found. Finally, this is the direct method, so the one currently working, and has been developed to let's say to put in one shape what previously learned from the previous developments. In this case, a full simulation is run where all the elements are simulated all over the whole track, but the simulation itself is split in many parts. So each simulation, let's say, could represent one corner of the track. Then there is an automatic post-processing, which allows the engineer to understand, let's say, in a short time, which is the problem and which is the actual structural situation after a whole track lap. This need of automation required obviously some implementation in scripts. Many scripts have been written, and they are, let's say, interacting one with each other. allowing for the interaction of many different software packages. Altair Compose has been chosen as a programming environment. So here we see a performance comparison between what developed so far. The first line is the most important and shows how the direct method and iterative method are actually the only one acceptable, since Abacus and history analysis are showing performances which are order of magnitude worse than the other two methods. Then there are other parameters which allow for the choice of the final method to use, which is the direct method in the end, thanks to its higher precision. It can be seen even in this picture, where the upper line represents the iterative method, where some peaks are chosen by an engineer. So it is an approximation, because the number of peaks and the precision of their identification depends on the time and on the experience available to the engineer. While on the lower row, we can see the direct method, which allows for a complete simulation of the timeline, and then allowing for an automatic post-processing. So it is, in the end, it's a complete simulation. Instead, the iterative method is an approximation. What can be said in the end is that direct method showed higher capabilities with respect to the other ones, other methods developed and analyzed. It satisfies all the simulation constraints presented previously, and its results are coherent with the iterative method. In the end, the direct method has been employed on a real model, so on a Formula One model, which has been previously analyzed by the Lara engineers, and has shown good results, so results which are in accordance with what previously found, even showing a higher precision level. This means that the direct method developed is a starting point for the analysis of vibrations in race cars and the modal dynamics analysis of car components. And that's it, and thank you for the attention.
Thank you for the presentation. Any question or curiosities from the Commission? Well, I have a curiosity about the method. So you told us that the many software are involved in the different steps of the application. Any issues in the connection between them? So very
yes.
often it is difficult to let them to talk each other.
Yes, in the end, the need of several methods development is also due to the fact that programs which belong to different software houses are not meant to cooperate. So it's quite difficult to have them to work together. In the end, this is this is not maybe the most efficient situation, the most efficient method, so the direct one, but is the only one which allows for a correct cooperation of different software, which could be Abacus, HyperWorks, and so on. So the pre-processor, post-processor, and that's it.
Yeah. What about the load? May you tell us something about something more about the load on the hardware that you need in order to support the method?
Yeah. I did not develop the measuring of the loads because it came directly from the Lara Dynamic department. But what can I say is that there are many considerations about the input data, especially for what regards the frequency of measurement, which is very important for the correct display of results. Because let's say that a low frequency accelerometer can generate a correct data, which is in the end approximate, generating a much lower level of stress. So could hide some criticalities which can be seen with higher frequencies. In the end, the measurement is quite easy because it is needed just a GPS on the car to measure the speed and an accelerometer to measure the acceleration which are happening on the chassis. And the aerodynamic load is measured through CFD, and the load distribution is coming directly from the aerodynamic department.
Thank you. Thank you so much.
I have a question. Sorry.
Yes, please.
Yes. Concerning the position of the accelerometer, of course, it is important where you measure this acceleration on the vehicle, and of course, which is the constraint that you apply in your model?
We applied an acceleration constraint. So we took let's say the frame to which the side mirror belongs to, which could not be displayed due to confidentiality issues. So it is a model belonging to Dallara. And by thinking to which is the real position of the accelerometer inside the car. So yeah, in the end, it's near the driver, right behind his back. By thinking to its position, we computed the stiffness matrix. So the stiffness matrix is needed to correctly link the position of the actual accelerometer in the car to the side mirror.
Okay.
The use of the whole chassis would have been too heavy for this kind of simulation, so stiffness matrix was needed. And the constraints. Okay.
Thank you.
Thank you. And so, Francesco, please stay with us because the next candidate is Simone Di Marco Berardino, and I don't see in the meeting the company advisor.
Yes, I think that the company advisor will intervene later in the discussion of the vote. So I can introduce the candidate as a university tutor. So Simone carried out his internship at FEV, that is a consulting company operating in the automotive field. And during his internship, he was involved in the studying how to experimentally characterize and numerically simulate the acoustic behavior of mufflers with the presence of flow. So the particularity of this study is the presence of flow in the study of acoustic behavior of mufflers. So please, Simone, illustrate your thesis work.
Thanks for the introduction. Good evening, everyone. In the next minute, I'm gonna talk about the automotive intake and exhaust system acoustic design, focusing on the flow acoustic interaction. I hope you can see me and you can see the screen and hear me clearly. Okay. In the last years, there has been significant changes and improvements in the automotive design, and noise, vibration, and harshness engineers are challenged with the system of growing complexity with a great impact on NVH performances. Recently, vehicle noise has gained importance for mainly two reasons. During the day, environmental noise has reached the alarming level of 75 dBA for half of the urban population, and the transportation system has proved to be the main noise source. Moreover, to reduce this noise pollution, the pass-by noise regulation, which limits the vehicle noise emission, are getting stricter. Nowadays, the car cabin noise is recognized by the final customer as one of the main vehicle quality factors. In the field of ICE vehicles, the engine system is the major source of noise, and in particular, the noise transmitted through intake and exhaust system is the dominant contribution. Intake and exhaust play a central role in the final vehicle interior and exterior noise. Therefore, their design is strongly connected both to sound quality and to environmental noise emission. Among intake and exhaust components, which are schematized here, the ones which can be specifically designed to control noise are the air cleaner box, muffler, and resonators. As already said by the professor, this thesis project is conceived to give a contribution in the silencer development by proposing a design approach where the flow presence is considered in the entire acoustic design process, from simulation to experimental characterization. Initially, the simulation tools which allow to predict acoustic attenuation with flow have been identified and studied. Then it has been designed a flow acoustic test rig specifically developed to perform acoustic measurement with flow and simultaneously determine the component back pressure. After having identified the required acoustic attenuation spectrum, the silencers are designed to meet the acoustic target, while at the same time minimizing the back pressure, which is the unwanted extra static pressure introduced on the engine intake and exhaust, which reduces its efficiency. Today, to simplify the design process, the acoustic attenuation performances are evaluated in static conditions without flow, while the silencer back pressure is evaluated in a separate phase. The performances of an acoustic silencer in static condition may not be coherent with the real behavior in operative conditions, where the flow presence alters the acoustic properties. The graph reported here shows the acoustic attenuation of the muffler in figure, with different flow velocities. This example is meant to show that the flow rate can have important effects, which may lead to an incorrect acoustic design. Therefore, it is important to consider flow in the design phase. The acoustic attenuation performances can be quantified with the transmission loss, which is defined as the difference between the incident and the transmitted sound power level. It can be also expressed as a function of the component transfer matrix. Moreover, transmission loss can be derived both experimentally and with simulations. The experimental determination starts from the definition of this equation, which represents the plane sound wave propagation in a duct with a viscous moving medium. But this equation holds true only below the cutoff frequency, where only plane wave propagates. The transfer matrix, which defines the relations between the acoustic variables at inlet and outlet section of a tested component, can be derived exploiting the plane wave decomposition, where the sound wave is decomposed in incident and reflected wave. Measuring the sound pressure with 4 microphones, the wave coefficients can be calculated and the acoustic variables can be derived. This procedure must be repeated, performing new measurements in different conditions, obtaining 2 sets of state variables. Finally, the transfer matrix of the sample can be derived and the transmission loss can be calculated. It is important to evaluate the transmission loss of a silencer before building the prototype to save both time and money. Here will be presented the acoustic simulation tools which allow to predict the acoustic attenuation performances with flow. Analytical acoustic method is based on the transfer matrix approach. The silencer geometry is subdivided into simple elements, each one with an analytical relation to calculate the associated transfer matrix, also considering the convective flow effect. Analytical method is really fast and can be used in an initial design phase. The main drawback is that it is accurate only for simple silencer and below the cutoff frequency because it considers only plane wave propagations. Within the CFD FEM coupled simulation method, the mean flow field distribution is derived with a steady CFD simulation. Then it is imported into the FEM acoustic model, which solves the linearized Helmholtz equation, deriving the silencer sound pressure field and transmission loss. This coupled simulation method offers accurate results, but it is complex and time-consuming, since it requires 2 simulations with different software. Instead of the coupled CFD FEM simulation, it can be used a full time domain CFD simulation. This method is a nonlinear method, and the Navier-Stokes equations are solved in time domain with unsteady simulations. And the resulting pressure time histories are then converted into the frequency domain with a fast Fourier transform. The CFD has proven to predict acoustic attenuation really well because it considers both the convective and dissipative flow effects. However, the computational effort is the highest among all these methods. One-dimensional CFD method is a simplified, version of three-dimensional CFD. With this method, the Navier-Stokes equations are solved only in one dimension, along the flow direction. This is much faster and simple to run. However, the simulation results tend to lose accuracy at high frequencies and in complex geometries because the three-dimensional wave propagation is not accounted. This last simulation method is very effective since it allows to rapidly estimate both transmission loss with flow and back pressure, completing the silencer preliminary characterization. In this slide is reported the simulation process with one-dimensional CFD software GT-Power, which I've used during my internship. The first step is to replicate the muffler geometry in the modeling environment. Then the three-dimensional model is discretized into a series of one-dimensional elements. The discretized muffler is then imported into the simulation models, which allows to solve for the transmission loss and back pressure simultaneously. Estimated transmission loss is compared with the experimental results obtained at 20 degrees with 10 meters flow velocity. As we can see, the correlation is really good. To conclude the process, another simulation is performed, but this time the muffler is in operative conditions at 300 degrees and with 100 meters per second flow velocity. The resulting transmission loss is much different from the one experimentally measured. This example has the purpose to show that experimental measurements are, on one end, fundamental to validate the simulation results, but on the other hand, they are not enough to predict the real behavior of an acoustic component. The aim of the flow acoustic test rig is to measure simultaneously transmission loss with flow and pressure drops. Starting from this, it is possible to identify the main functional component of the bench, which are collected in this layout scheme. After having established the general configuration, the performances requirements have been obtained thanks to FEV internal know-how, technical research, and surveys proposed to possible future customers. Since the bench will be used to test also more components together, even the entire intake or exhaust assemblies, three side channel blowers will be used, since they are capable of generating high pressures and providing flow rate in both direct and reverse direction. Right after the blowers, a laminar flow sensor acquires and checks the flow rate value. One of the main problems linked to this kind of benches, flow acoustic benches, is that the flow-generated noise introduces unwanted reflections and disturbances in the acoustic measurements. Therefore, the acoustic source has to provide a sound pressure level which is 10 dB higher than the flow noise to ensure a good signal-to-noise ratio in the entire measurement frequency range. Two medium compression drivers will be used as acoustic source. With a sweep sine signal, they are capable to generate a broadband sound pressure level which is higher than 130 dB for the entire measurement frequency range. This should be enough to dominate the flow noise, but this aspect can be confirmed only with experimental tests. To attenuate the flow-generated noise, a muffler will be mounted after the flow meter and another one on the opposite side of the bench, in this case to reduce the noise radiated into the workplace. 6 side-vented condenser microphones will be used to acquire the sound pressure level required for the transmission loss computation. Pressure and the temperature will be measured with a differential pressure sensor and a thermocouple. All the sensors will be connected to the data acquisition system from which the measurements results will be collected. In parallel with the test rig development, it has been created a GT-Power model of the bench, which has been used to perform parametric analysis useful to define some design aspects related to the bench itself. To perform this parametric analysis has been simulated the muffler already studied before with a simple GT-Power model, and whose transmission loss has been already validated with the experimental measurement, setting a reference curve. The first parameter studied is the length of the side duct, which connects the compression driver to the main bench duct and introduces unwanted reflections. graphs are collected the transmission loss curves obtained with different side duct lengths. As we can see, the side duct introduces oscillation and deviation in the curve. And on the other hand, you can see that the trend is clear. As the length decreases, the oscillation decreases. Therefore, the best result has been obtained with the shortest length possible. This design aspect is also confirmed by literature references, which suggest to flush mount the compression driver directly on the bench main duct and to use between them a highly perforated cover, which is acoustically transparent, both to minimize the flow generated noise by the interface and to protect the driver. Before going on, it should be remarked that the main duct of the test bench has a fixed diameter, while the test element has a diameter which varies every time. To avoid a sudden area discontinuity, a conical adapter is used to switch cross-section. The discontinuity introduced by the conical adapters is related to the divergent convergent angle, which is the second parameter studied. 5 different angles have been tested. By observing the graphs, it is possible to notice that the presence of the conical adapters introduces deviation on the curve, but in particular in the low-medium frequency range, where the transmission loss value is increased. Both in the transmission loss associated to 1 and 1.9 degrees, these deviations are minimized. Therefore, to reduce the conical adapters effect, the angle should remain low between 1 and 2 degrees. This parametric analysis concludes the design phase of the flow acoustic test rig, which is now ready to be assembled. With the test rig, it will be possible to assess the acoustic attenuation performances considering the flow effects and simultaneously measure the back pressure. Then the experimental results can be used to validate and tune the simulation model, allowing to simulate the silencer in operative condition, both flow and temperature, helping the MVH engineers in the acoustic design of the silencer. Thank you for the attention.
Thank you. Thank you for your presentation. Any question from the Commission or any comment? No, your presentation was very clear. I have just a curiosity, if possible. Obviously, this is part of the problem. I mean that after such kind of simulation, you have to consider many other constraints due to the manufacturing, for instance, or the constraints that you have when you assemble the part. Have you got the possibility to consider also such an aspect during your development? So do you have some preliminary information about the manufacturing limits or the assembly limits that you have to face?
Related to the design of the bench itself or to the component production?
To the component or to the system as a whole?
Yes. Unfortunately, I haven't had the occasion to personally measure these devices because my thesis was just the design and simulation. I haven't touched any microphones or, let's say, experimental devices. For this reason, we haven't deepened this aspect. But surely these little defects can only be noticed when testing the component experimentally. It's really difficult to, for example, welding defects which may alter the acoustic properties, but it is really difficult to spot this kind of defects on simulation and understanding their effects, especially with the simplified simulation models.
Yeah, for sure. It's a very preliminary analysis of the problem. So thank you so much for your answer. And I ask to the next candidate to prepare the presentation. That is Nicolò Ferrari. And I see the company advisor present into the team. Is it right?
Yes, I'm here.
Yes, so I don't know if you want to introduce the candidate.
Yeah, sure. Good afternoon. I am pleased to introduce the next thesis. The candidate carried out his work in the Ducati prototype department, where he faced a common and at the same time tricky problem: the human being comfort objectivation. We live in an historic moment in which the time to market is year after year reduced. And for the design and optimization of stuff. So I leave you the word, Niccolo.
Thank you very much, Mirko.
The audio was not so clear, but I think that we all catch some words for the introduction. So please, Niccolo, start your presentation now.
Thank you, Professor. I will share my screen. Can all of you see the screen I'm sharing?
Yes.
Okay, perfect. So first of all, I would like to start by thanking engineer Mirko Maurici, and also my supervisor, Professor Marcello Vanali. As Mirko introduced, the subject of my thesis is the parameterization of the saddle comfort through the use of machine learning algorithms. So I would like to start by introducing comfort. Comfort in the last year has become fundamental not only for touring motorcycles, but also sports-oriented motorcycles. For example, the ones of the naked category and super sports category. And mainly this is due to three reasons. The first one being that comfort influences the so-called perceived quality of a product. And the customer, it has been proven that the customer is willing to pay more for a higher quality product. And not only this, which means more sales for the company, but also comfort is really connected with customer satisfaction, because many riders usually buy a motorcycle and tend to modify or completely replace the standard OEM saddle with an aftermarket solution. So the first step that we did was evaluate comfort. How can we evaluate comfort? So comfort is a sensation that is connected to the human body. And for this reason, we had to study the human anatomy, in particular, the region of the buttocks. In this region, we have fat, muscles, and most importantly, nerves, such as the one of that usually causes sciatica or lumbar pain, and also bones. In particular, for our study, we focus our interest on the ischial tuberosities. In order to evaluate comfort, we can work with objective data, such as the use of test rigs to, for example, measure hardness, relaxation, and creep, or, for example, the analysis of the ergonomics. So, for example, the geometry of the handlebar, foot pegs, and seating point triangle. But we can also use pressure mats to evaluate the contact area and the pressure distribution, pressure peaks, and standard deviation. And finally, we can evaluate subjective comfort through the use of motorcycle seating comfort questionnaires. The first task that I had to address when I arrived in Ducati was the development, together with Mirko, of a new indenter, a new tool to be used on the test rig. As you can see, the original tool is not, does not replicate in any way the shape of a human body. And as you can see, the pressure distribution is completely useless from this point of view. So we developed a prototype. The first one was made out of silicon, because we thought that silicon would have been a good material to replicate the human flesh, so the muscles and soft tissues. However, this was not the case. It only added an additional level of uncertainty in the testing, because it was not easy to predict the stiffness of silicon. So we decided to produce a final tool in a stiff material called UREL, which can be easily machined. And this on the right was our final solution. Then we had to develop a new testing methodology. In a static testing methodology, we started with a subjective evaluation panel in which we had 9 motorcycles and 20 subjects, 20 volunteers. we had them to test every motorcycle, and we acquired pressure distributions through the use of the mat. And then we had them to fill a motorcycle seating comfort questionnaire. Then these 9 motorcycles are tested with a test rig. We used, as you can see in the central picture, the new anatomical indenter, and we followed a new series of testing standards that we developed in-house. Finally, we also started working with data analysis to understand all the data and to find, let's say, correlations and useful information. We worked with conventional analysis and also with machine learning algorithms. The first thing that we did in the data analysis phase was to find a correlation between subjective evaluations, such as the overall seat comfort, or, for example, the seat cushion firmness and the pressure under buttocks, and correlate these values with the objective data recorded with the mat. For example, the area, the peak and mean pressure, standard deviation, and load. And we found already some interesting information, such as that the area is fundamental. A higher air contact area yields to a much more comfortable position, comfortable saddle, sorry. And on the contrary, load is completely uncorrelated with comfort because it's solely collected with the person that is testing the motorcycle. Moreover, for example, peak and min pressure are connected with pressure under buttocks, of course, but also with the seat cushion firmness. And standard deviation proved to be very important because it gives an idea of the distribution and how evenly distributed is the contact surface. We understood that there was still something missing. We understood that the saddle is not the only component that qualifies comfort for a motorcycle, but the ergonomics are very important too. In this case, you can see the so-called ergonomics triangle, in which we have the seating point, which is the origin of our graph. Then we have the handlebars and the foot pegs. And in this case, we focused on 4 motorcycles of the naked category. And I would like you to focus on the Ducati Monster 936 and the Triumph Street Tripole, which are the blue and the orange one. The Triumph Street Tripole had amazing numerical data, probably the best in the category. However, it turned out to be not the most comfortable motorcycle. The most comfortable one was the Ducati Monster 936. And this is because, as you can see, especially the handlebar position of the Triumph is much lower, and therefore the body, the upper part of the body, is more forward oriented, meaning that the rider feels a sportier stance, however, lacks a little bit of comfort. And in the end, the Ducati proved to be a much more comfortable solution. Then we started working with the basic and simple machine learning algorithms, such as the mono and multivariable regression. We used both linear regression and polynomial regression. And the first thing that we did was studying the correlation of one single variable with the individual evaluations, such as the one you can see on the right. As you can see, since this is a subjective evaluation, the data is not very clean and pretty widely spread. However, we found some acceptable results. On the contrary, we did the same studies by correlating multiple variables and seeing, since such as, for example, the contact area and the contact pressure, and since this is just purely objective data, the results were pretty straightforward and perfectly understandable. Then we decided to use a little bit more complicated algorithms, such as neural networks. We worked with a shallow neural network algorithm, which had the target to predict subjective comfort starting from objective data. The objective data that we used was pressure images, mechanical properties, mechanical data obtained from the test rig for the saddles themselves, and also all the pressure distributions, contact area values of the subjects during the test. We fed this data to the neural network system, and we tried to predict a comfort score. However, we found that our system was overfitting. Overfitting is a well-known problem in the machine learning environment, and it happens when we have a very precise, so high accuracy on the training set. However, it has a low accuracy on the test set. There are many solutions which we tried. For example, we did some lambda tuning and regularization, which proved to increase a little bit the accuracy. Then we also worked with network simplification, early stopping, and data augmentation, which unfortunately did not yield any improvement. And finally, we worked with standardization and normalization of the data, which we then fed to the algorithm. And this also helped a little bit. However, the final result was still not acceptable because a testing accuracy of 65% is not reliable enough to be confident and use this tool as a development tool. So we had to understand that the problem was to be found somewhere else. The problem, we thought, could have been the data quality. In fact, since we worked with volunteers, they had different body anatomy. So for example, different body weight index, which is the ratio between the height and the weight of a person, but also different fitness level. Very importantly, different riding experience. Some of them were professional testers for Ducati, and others never rode a motorcycle in their life. And also there was a problem of personal sensitivity and perception. So to better understand this, I would like to show you these 4 pictures. On the right, we have 2 male and 2 female, 2 with low body weight index and 2 with medium or high body weight index. And as you can see, they're very different. And 2 different pictures, so for example, the 2 men might give the same evaluation for the same motorcycle. Or for example, 2 similar pictures, such as the 2 on the top row, might give opposite evaluations for the same motorcycle. So the algorithm really struggles to understand what prediction it has to do. So although the neural network did not prove to be suitable for this tool, for this task, we were able in these months to develop some very useful tools for development. For example, the new indenter that I explained before, or for example, the fact that we created with these kind of tests a suitable database for saddle design and improvement. But with linear regression and polynomial regression, we were also able to have some simple tools that were able to predict the comfort quality of the new saddle variations. And unfortunately, as I said before, our neural network system did not prove to be very effective. So in conclusion, I would like to say that unfortunately, comfort is extremely subjective. And in our case, due to this variation of data, we have to work with simple tools. In our case, the neural network was not very useful, but these simple tools provide to be pretty effective. Thanks to these new methodologies, we are able to parameterize comfort, however, not in an extremely accurate way. So we will never have 100% accuracy, simply because subjective means very different from one person to another. So in my opinion, the future lies in custom solutions for the customer, in which the engineers cooperate with the customers themselves and develop solutions and saddles with different designs and saddle stiffness in order for them to have the ideal comfort level and allowing them to ride for many thousands of kilometers without any kind of issue. Thank you for the attention.
Thank you. Any question or curiosity from the Commission?
I have 2 questions.
Yes, please.
So the first one is, I imagine that the vibrations of the arms transmitted by the handlebars also affect the comfort. So have you also studied this aspect that, of course, is related to the global results of the test, the subjective tests?
Yes, exactly. There are many more factors that influence comfort. As you said, vibration is one of the most fundamental aspects that affect comfort. We studied them, but we did not do any kind of test, simply because we worked on the analysis of static comfort. Also because we found some very interesting academic research that shows that for a long period of time, long periods of time, static tests are efficient to predict dynamic tests if the pavement, so the road quality, is not harsh. So in our case, since we worked with sports-oriented motorcycles, we were pretty confident that the customers would not go riding off-road. So we assumed that studying the problem from a static point of view would be a first acceptable step in order to qualify comfort as a whole. Of course, in the future, if a perfect work needs to be done, then we will have to consider vibrations, both from the handlebars, but also from the saddle itself. So the transmission of vibration from the wheels to the saddle and to the human body. So yes, it has to be considered, but we did not consider it in our testing phase.
Okay, so you probably answer also to my second question, that was about the analysis of the pressure. It's a static pressure, it's a time domain pressure, or also a frequency analysis of the pressure?
No, it's a time domain analysis. We did two different tests. For example, when we tested the static position of the subjects, of the volunteers, we acquired only one simple frame. So the rider was standing still and we would acquire a frame. Then, in order to study more deeply the aspect of pressure, we also put the pressure mat on the test rig during tests on the complete motorcycle. And in that case, we tested for the whole test. So the test was around 10 minutes because, of course, we have to replicate some real environments. So it's not just a single acquisition, but for example, a 10 minutes acquisition, so that we could work also with more data and have a complete, let's say, data set also that considers different kind of loads.
And this was a laboratory test and not a road test?
Yes, unfortunately, we were not able to perform road tests, so we had to work only in the lab. Exactly.
Okay, thank you.
Thank you.
Thank you so much for such an interesting presentation. My first motorbike many years ago was a Monster, and I remember that the saddle was not the best point of the bike. So I'm sure that there is many good results to discuss with you for the future.
Sure.
Good. The next candidate is Alfonso Iezzi.
Thank you.
Good afternoon. Here I am.
And Davide Pontara, thank you to join us. So
good afternoon.
Please introduce the candidate.
Yeah, as I agreed with the company advisor, I will introduce Alfonso. So Dr. Iezzi's activity is part of the electrified fleet development in Maserati. And in particular, he developed a new design tool which allows to simulate the electric components and the energy flow between them. So basically, the activity consisted in the development of analytic models of the electric components, a proper calibration of those models, and then a validation of the entire simulation system by means of testing. And the achieved result is a very flexible tool, as it allows to simulate either standardized cycles as well as customized profiles in order to test different operating conditions and support the development of control strategies for new electrified powertrain architectures. So please, Alfonso, you can start with your presentation.
Thanks, Professor, for the introduction. Is it visible? Can you see something? Can you see?
Yes. Yes.
Okay. Well, good afternoon, everyone. I'm Alfonso Iezzi, and today I'm going to present my thesis work regarding the modeling of the low-voltage system of electrified vehicles. First of all, I'm going to give an overall context of the work and then enter into details of the model, passing through its implementation, how the components were characterized and their model validated, and then conclusions and further improvements. An electric energy balance test is a procedure where the electric flows among the main components are measured. This homologation test is done in order to check if the charging devices are suitable to ensure the onboard charge of the battery in the most heavy-duty applications. These conditions are represented by missions performed downtown with intense traffic and thus predominant start and stop. Although effective for reduction of pollutant emissions, the start and stop is still one of the most stressful phases for the electric system. The energy balance test is standardized and can be either performed on road or on a roller test bench. The aim of the thesis work was to reproduce this type of test in a virtual fashion, so using a model of the electric system. The use of virtual simulation has become very useful when dealing with complex systems. This is the principle of the model-based design approach, and the technique under evaluation is the model in the loop. While the electric energy balance test is a pure validation step where the system is certified to be compliant to initial requirements, the model in the loop is a part of the verification phase that allows the research of the optimal design parameters by running iterative simulations of the virtual model. In our case, this means find the best trade-off and the best evaluation, the best parameters for the evaluation criteria of the electric energy balance test. One of the most important is the state of charge of the battery at the end of the test. This leads to reduction of validation test on physical component. The focus was set on the electrified fleet. In particular, the tested vehicle was a P0 mild hybrid electric vehicle, a type of parallel architecture where the main electric machine is placed at the beginning of the driveline, before the crankshaft. Among the other hybrid architecture is the one with the best trade-off when considering an integration on an existing platform based on an internal combustion engine powered car. This vehicle is characterized by the presence of two electric systems working at different supply voltages. The 48-volt system is composed of a lithium-ion battery, the BSG, also known as Bell-Star generator, so a kind of advanced alternator, and the e-booster, which is a compressor driven by an electric motor. Instead, the 12-volt system is composed of a lead-acid battery, a standard automotive one, and the electric loads, defined as all the components that, in order to work, drain current from the system, with the exception of the ones related to the tractive effort, such as the BSG and the e-booster. In order to connect together the two DC buses, a DC-DC converter is used. The first step was to build an equivalent electric circuit representing the model through lumped parameters. Then the following step was to implement a high-level representation of this circuit in the multiple Simulink environment in order to be able to perform simulations and thus predict the electric flows and the state of battery. We started from a blank paper and concentrated our efforts on the low voltage system because the final target was to analyze the lead-acid battery during the electric energy balance test. With this assumption, the model can be easily adapted to each kind of hybrid architecture and even to full electric vehicles. Therefore, the Simulink model is composed of a 12-volt lead-acid battery, the electric loads, and the DC-DC converter, which can be modeled as a ideal voltage-controlled current source. Each of the three components was characterized, so it was stimulated to find mathematical and analytical expressions representing its working behavior. So a deep knowledge of the component was necessary to achieve good results. The battery, the most difficult to be modeled due to the inherent complex and nonlinear behavior, was characterized through a set of pulsed current discharge and recharge tests using programmable devices such as the electronic load and the power supply. It was considered again an equivalent circuit representation, so a linear structure composed of electrical parameters. The dependencies of these parameters on the state variables, such as the state of charge, were obtained through this pulsed current test and are represented with lookup tables, so with maps, and with parametric expressions. The battery model computes the battery voltage depending on the input current and on the state of charge of the battery. And it's very important to have an accurate voltage output of the model because the converter operation is based on that. The following step was the battery model validation, not to be confused with the validation of the V-cycle. The battery was the only component that was validated standalone, and then the battery voltage and battery current were measured during a custom cycle. Then the measured current was used together with the initial state of charge as input for the simulation of the model. The simulated voltage output of that model, of the battery model, was then compared to the real voltage signal, so the measured one, in order to quantify the accuracy of the model. Of course, the more the fit between these two voltages, the higher the accuracy of the model. Instead, the electric loads were characterized on board through a manual activation and deactivation in order to quantify the current absorption of each component and a typical activation profile. These activation profiles are represented with a vector representation, and since the biggest part of these loads is manually activated by the driver, in order to make an objective evaluation of the electric energy balance test, standardized profiles were taken as reference for the simulations. They represent the largest customer percentile usage, so a common usage, and are divided depending on the selling country, so they highly depend on the ambient temperature. Finally, the converter, that is the main responsible for battery recharge through rule-based strategies. It is modeled as an industrial PI controller. Indeed, it works as a voltage follower, meaning that the converter output, that is the downstream current, is regulated to follow a given voltage set point. In turn, the voltage set point depends on the level of state of charge of the 12-volt battery. Therefore, the lower the state of charge of the 12-volt battery, the higher the voltage set point and higher the current that recharges the battery. Different numbers of state of charge windows were evaluated, considering also hysteresis between switching values. The voltage set point refers to the converter voltage, and the converter voltage and the battery voltage can be considered almost equal unless a little voltage drop due to wire resistance that, however, was accurately measured and accounted within the model. The validation of the overall model was carried out by comparing simulation results with real data signals obtained running a real energy balance test. This was made possible because the model allows to define custom speed and custom electric load current profiles other than the standard ones. The initial requirement was a maximum error between estimated state of charge from the simulation and estimated state of charge from the real test below 1%, having considered both CAN discretization and error calculation from the battery management system. Despite some strong hypotheses that were made, as you can see in the figure, this requirement was fulfilled. So, and therefore, this predictive simulation were started. The overall model is parametric, and rather than modifying the MATLAB code, which the Simulink model is based on, a graphical interface allows to easily change the design parameters and analyze their effects on the output electrical quantities. In this way, it's possible, for instance, to choose the operating points of the battery so that it can work in its optimal range. Here, the most influencing tunable parameters are related to converter and start-stop strategies that, as I said at the beginning, are very important when dealing with the hybrid vehicles. The graphical user interface, as well as the MATLAB code and the whole model, were built from scratch. Here are two main improvements that can be considered in the future. The first point concerned the thermal model of the battery that was already implemented, so the missing part is the characterization part that is possible only using suitable climatic chambers. The second point instead is related to the modeling of the remaining part of the electric system, the one at the higher voltage. That, of course, depends on the vehicle architecture considered. Only in this way is possible, of course, to have an overall sight of the electric flows within the vehicle. And that's all. Thanks. Thank you for your attention.
Thank you. Thank you so much for the presentation. Question from the Commission? Any comment? So thank you. The presentation was clear enough for all the members of the commission.
Thanks.
So,
thank you. Thank you.
Thank you again. And the next is Francesco Marchiano.
Good afternoon, everyone.
Good afternoon. And I see Paolo Perello.
Hello, everyone.
Yes. So, please, if you want to introduce shortly our candidates.
Yeah. So Francesco Marchiano spent something like 6 months here working at WICOM, developing this project. This project, the aim was to investigate fiber optic sensors to map, let's say, the structural integrity and the structural behaviors of components, which are tested under load. So what he did was to understand the technology and understand what's on the market, then passing through also firm analysis and engineering study, understand how to try to test this kind of systems, and then developing a practical side of his final thesis was to produce these samples, test them, and so evaluate the technology, and get to a final test of a push-off of a front pressure for a Formula 4 car. He did it pretty well. We are happy with the job done, and also because it made us understand even more the engineering issue and the engineering limits that actually a simulation can offer. So I will let him explain the job done. Thank you.
So thanks, Paolo, for your introduction. I would like to thank also my supervisor, which was the Professor Vanali. And as introduced, the main objectives of the thesis work was the assessment of the strain readings reliability of the fiber break rating sensors, and different installation techniques on composite were analyzed in order to perform a structural health monitoring analysis in terms of strains and stresses mapping. This was done through the analysis of some simple laminates bending tests, and finally a test was performed on a Formula 4 front crash box of a push-off test. As said, the material used during the thesis work are carbon fiber reinforced polymers. So as each composite material, they are composed by 2 distinct phases, a matrix and a reinforcement, a polymeric matrix and a reinforcement. And the main advantage related to the use of this material is the possibility to tune their properties according to the needs. So it is possible to achieve very high specific strength and stiffness, which allow for the construction of very lightweight structures. In particular, the material used during the current work was a thermoset epoxy resin coupled with carbon fibers arranged as a woven or continuous and aligned fibers. The core of the analysis was the assessment of the reliability of fiber break ratings, which are sensors inscribed on fiber optics, capable, when interrogated by a wide wavelength range incident spectrum, to reflect back just a narrow range of the wavelength of the incident wavelengths. So this reflected spectrum depends upon the periodicity of the fringes inscribed on the fiber, and depending on how it is, and depending on the solicitation felt by the sensor, these fringes may be deformed, and this is detected by monitoring the reflected spectrum of the fiber break rating. The main advantages related to this kind of sensors are their immunity to the electromagnetic fields, along with the possibility to multiplex them along the same fiber and to embed inside the composite materials. On the other hand, they may suffer by birefringence phenomena and temperature sensitiveness. The experimental setup used for the laminates bending test is shown in the current slide, where a comparator and a potentiometer were used in order to monitor the deflection of the composite laminates, while some electrical strain gauges were adopted as absolute references for the FBGs. The loads were applied through some calibrated weights, tightened to a screw and positioned in correspondence of the whole of the specimen, while an interrogator was adopted in order to interrogate and acquire the reflected signal of the FBG. The different tests performed aim in simulating different installation techniques of this kind of sensors, even if the geometry of all the specimens is the same of the one reported in the current slide. So a first test was done at the beginning in order to characterize the bending behavior of the specimen. Afterward, it was considered in the second test the integration of an FBG between two collinear prepreg sheets, and two additional FBGs were bonded on its external surface. One of them was also covered by an end-laid up composite stripe in order to thinking about possible dynamics installation. In the test C, two different FBGs were embedded in the specimen. One was packed between two UD stripes in order to ensure a collinear surroundings to the sensors, and it was the one towards the mold side, while the other one was equivalent to the test B embedding technique. While in the last one, the FBG was embedded between two non-collinear prepreg sheets, and in particular between a 0-90-degree ply and a 45-45-degree ply. For each FBG used, there was an electrical strain gauge adopted as absolute reference of the strain measurement. So it must be said that embedment techniques is not so straightforward because some failures may occur during the autoclave processes and mainly related to the temperature and pressure achieved in the autoclave. In particular, the resin outflowing from the prepreg sheets may embrittle the fiber, causing some failure in correspondence of the exit from the specimen. These problems can be easily avoided just placing a rubber-like material in correspondence of the fiber exit, which vulcanizes at the temperature reached in the autoclave and protects that region of the fiber during the process. At the same time, also the pressure applied in the autoclave may lead to some failure close to the connector of the fiber, but also this issue can be avoided just taking out the connector from the vacuum bag. During the analysis, a simple FEM model was developed in order to predict the strain and stresses felt by the structures. So the model was based on a conventional shell element to represent the specimen lamina, and a composite layup was enforced to describe the lamination sequence of the prepreg sheets laid up. The load was imposed in correspondence of the center of the hole, which works as a reference point and transmitted to the external circumference of the hole through a kinematic coupling, while the boundary condition imposed was a clamp on the other side of the specimen to represent the real test boundary condition. So let's start to analyze the experimental results achieved during the analysis. All the graphs that we will see will have the same representative state shapes because it is directly related to the sequential loads application. The first step is just the comparator positioning, while all the other one are each step related to one of the calibrated loads seen in the previous slides. This test, as said, was just worked as a reference for all the other one, and it is used to validate the FEM model described. In particular, it was possible to verify how the strain readings of the sensor in this condition differ from the one predicted by the FEM for a value lower than the 3%. So the model is considered valid, and this range remains almost the same for all the other specimens besides the test D. In the test B, as said, one FBG was embedded between two collinear prepreg sheets. So the strain acquired by this kind of sensor are much lower with respect to the electrical strain gauge installed on the surface, just because the sensor is closer to the bending neutral plane of the specimen. Anyway, its qualitative behavior perfectly matches the one of the strain gauge. But it must be remembered that if this kind of installation is adopted, a certain scale factor must be imposed to match the true readings of the sensor. The scale factor depends upon the true thickness strain slope of the deformation of the specimen, which is directly dependent upon the prepreg sheets interposed between the two sensors and their mechanical characteristics. At the same time, the embedment of the sensor causes a stiffening of the laminate because of the agglomeration of resins which are created around the region of the fiber optics, and it can create some issues when considering some cyclic loadings. When dealing with the two FBGs bonded on external surface of the specimen, we can see how the orange curve, which is related to the FBG naked on the specimen tested, perfectly matches the one of the electrical strain gauge, while the other one, which is the one covered by an end-laid up stripe of composite, shows a small shift with respect to the other sensors, which is induced by the localized stiffening induced by the effect of the composite stripe, and by the fact that the sensor is not measuring anymore on the outermost surface of the specimen, but it is placed one layer below the outermost surface. Anyway, their qualitative behavior perfectly matches to the one of the electrical strain gauge. When dealing with the test C, in the test C we have 4 curves in each graphs because we have 4 sensors installed, which correspond to the 2 FBG sensors and the 2 strain gauges. In particular, the FBG towards the mold side of the specimen is also packed between the 2 UD stripes. The installation, placement of these 2 UD stripes causes a non-symmetric behavior of the specimen, as we can see on the plot on the left, where the strain reached in tension and in compression by the specimen are not equal, because it moves the neutral plane of the specimen towards the mold side. Anyway, it seems not to induce any beneficial effects in the reading of the FBG, which perfectly matches the one of the electrical strain gauges placed on the outermost surface, even if it is not placed between 2 UD stripes. This specimen was also tested flipping its orientation in order to verify if the behavior in tension of compression of the FBG placed between the 2 UD stripes and of the one placed directly between the prepreg sheets may suffer from any particular phenomena. But anyway, the results achieved by both the tests are perfectly aligned if we consider the correspondent sensors of the 2 tests, so the same color curves. So it means that both the FBGs installed works better both in tension than in compression. The last test performed, which was the test D, considered the embedment of an FBG between 2 non-collinear prepreg sheets. And this test results to be the only one where the strain readings during the experimental test are completely not aligned with the simulation. So it makes think that the problem was not the model and the correlation of the simulation, but it's the readings of the sensor, because in this case the FBG is not capable to isolate the strain felt by the 0-90 degree plies, because it suffered the side effect induced by the differently oriented prepreg sheet placed below the sensor. So at the end of this analysis, it is possible to state how the embedding techniques furnish very reliable results, besides the last one considered between non-collinear prepreg sheets, but the time and cost related to the installation and the production of composite materials installing this kind of sensors during the lamination process is not affordable for a motorsport environment. So the external installation seems to be the best compromises between time and cost achieved and reliability of the measurements. So this is the reason why these 2 installations are further analyzed in the last test performed, which is an indoor testing, a push-off of a front crash box of a Formula 4 car. The setup of the test is shown in the current slide, where the nose is bolted on a steel plate, which is fixed on a test rig, and the load is supplied sideways by a piston actuated by an hydraulic pump manually controlled. On the free side of the nose, there are 2 sensors installed, one FBG, which is the one covered by the end lead-up stripe, which is coupled with an electrical strain gauge working as a reference, while on the piston side of the nose, there is a naked FBG, which is the sensor on the left where the glue is visible, coupled with another electrical strain gauge working also as a reference. It must be said that once the nose is bolted on the plate, at least one loading-unloading cycle is needed in order to let the structure settle. This is visible when analyzing the first loading cycle applied to the structure, where the sensor starts from a 0 strain, and even if the structure is working in a completely elastic field, the final strain revealed by the sensor has a certain shift between the 0 and 1. Anyway, in both the loading cycle applied during the first test campaign show how both the FBGs perfectly match the readings of the electrical strain gauge. Also in this case, the FBG mounted on the free side, which is the yellow curve, has a slightly higher shift with respect to the strain gauge because of the presence of the composite end lead-up stripe, which covers it. Repeating the same test a second time, it is also possible to assess the repeatability of this kind of measurements, because looking at the plots on the right, also the absolute values achieved, both in tension and compression, perfectly matches the one of the first test campaign if they are cleaned by the settlement strain discussed. So at the end of this analysis, it is possible to state how during the thesis work, the best embedment techniques and they was tested and defined, but they resulted to be not the right way to pursue in a motorsport environment where the time of production plays a very important role. So an external installation seems to be the best compromise for the application of these sensors. And what it is left open for future development is the onboard mounting of this kind of sensors on a car, and their interface with existing ECUs in order to assess and verify their reliability during dynamic test condition. So that's all. Thanks for your attention.
Thank you. Thank you for the presentation. Any question from the Commission? I ask you to close the sharing of the video at the moment. Yes. So, thank you. So,
can I ask you a question? I'm Gianni Nicoletto.
Yeah, sure.
Yes, my question is related to the applicability of this FBG sensor. As I saw that in the last pictures, the application was on the outside of the component, on the surface of the component, very much like in the case of a strain gauge, which was glued on the side. What is the advantage of using the FBG compared to a standard strain gauge with this kind of application? Is there any, accuracy or some other reason why it would be preferable to a strain gauge?
Yes, one of the main reasons why these sensors are better than a simple strain gauge applied externally is the fact that they can be multiplexed on the same fibers. So it is possible to have a single fiber measuring in a sort of a distributed measurement along the fiber, where with different points of measuring, and just one input and output is needed. In addition, the fact that we're just measuring the reflected spectrum allows just to have one fiber running on the component. While considering strain gauges application, if I want a measurement in more points of the structures, I need for each strain gauge at least one cable going to the strain gauge and another one coming out from the strain gauge to be acquired.
Okay. Another question is, you buy strain gauges with different sizes. In this case, how localized can be the strain measurement in the case of BFG? With the strain gauges, you can go down to gauges that are long a few millimeters. And yes. So to measure really on a point, almost on a point, the material response. What is the limitation in terms of the localization of the strain measurements with the BFG?
The FBG using during the analysis have a length of 8 millimeters. But the main issue is related to the manufacturing process, because the position on the fiber of the FBG is not perfectly known, because the manufacturer gives an indication of 3 centimeters through blue segment on the fiber, and it states that in between these two segments it is placed the FBG. So there is a certain uncertainty related to the manufacturing process, which cannot be overcome.
Okay. Thank you very much.
You're welcome.
Thank you. Thank you, Gianni. Thank you, Francesco. So we can move to the next candidate. That is Gabriele Pinelli.
Yes, good afternoon. Can you hear me?
Yes, perfectly. I don't know if was able to join us. Yes, here you are.
Yes.
Hi, Nicola.
Yes, hello to everyone. I had the opportunity to work with Gabriele, and was a very good experience because we worked together with something new for both. And I was really impressed by Gabriele, by his ability to focus on a problem, on a real manufacturing reality, and to be always accurate and very clever in some choice. So it was a very good experience. So Gabriele, good luck, and have a fun your professional experience for the future. So it's your time now. Thank you.
Thank you. Thank you, Nicola. I'm going to show you my screen. Can you see it?
Not yet.
Not yet. Okay. Now can you see it?
Yes, perfectly now.
Okay, perfect. So, good afternoon to everyone. I'm going to talk about my work thesis on the development of a framework for performance and reliability analysis of an hybrid transmission for hypercars from the end-of-line testing, and with the investigation of artificial intelligence. So today I will talk about initially about the introduction of the problem. Then I will describe the end-of-line testing. And then I will move to the discussion about the development of the software for data analysis that I perform. Then I move to the offline analysis of this software and its relative results. At the end, I will discuss about some investigation that we decided to perform with the artificial intelligence for few strange cases. And at the end, I will talk about the conclusions. So, starting with the problem introduction, we have to say that the introduction of hybrid technologies was a very hot topic for car manufacturers, and we have to take in account that this kind of technology increased the complexity of the systems. So it's necessary to have a good control on the reliabilities of those systems, but it's not always so simple, mainly for a limited series of hypercars, like in this case, because the smallest batch of production. So in order to have to allow this control on reliability, it was performed an end-of-line test, and now we are going to see how. So the end-of-line test is structured as follows. So basically, you start from the assembled components, and you set the assembled components on a specific test bench that has a list of tests that allow to verify all the functionalities, or mainly the most important functionality of the system. And each test has a pass-fail criteria, and if all of these tests has a pass result, the component can be considered okay, and it's delivered to the customer. If even just one of them is failed, it's necessary to stop the product and to analyze in offline all the data in order to understand what happened and which are the reason of this failure. So the first point necessary to improve the control of the end-of-line procedure was the following: the development of a software for data analysis. So we have to say that the output from the end-of-line test was a TXT files that contains all the information and all the data. It was necessary to use this software, first of all, to create a storage, a Unix storage that collected all these informations and this data. So the idea was to develop this software to extract from TXT files all the information and create a structure in object-oriented of the storage of the entire dataset. This was a very good plus for the system because it allows to contain everything together and allows to have access to all the information in a very easy way. Then I allowed the software to perform offline data analysis. This is a very important point because the goal of this analysis are two. One is the refinement of the system, modifying the pass-fail criteria. The second one is to define and check some anomalies. And moreover, this kind of analysis has another good point because thanks to the storage that I introduced before and everything together, it's possible not only to perform an offline analysis on one single test per time as previously done. Now it's possible to compare all together all the tests performed during the time. So we have all the storage and all the history of production together. And this was a very huge advantage for the data analysis. Moreover, for the software, it was necessary to develop a graphical user interface. This is a very powerful tool that allows to interact very easily the user with the information and the data. As you can see from this picture, it was split in three main groups. The first one on the left, in which you can easily select the kit and the test that you want to analyze. On the right, you can choose all the channels that you want to look, and you can simply visualize them, or you can choose to apply an analysis that was collected inside the software. Basically, during this period, we developed a lot of offline analysis, and they were collected inside the software. Thanks to this, it was possible to replicate the analysis whenever we want. So this tool was extremely useful for improving the analysis and achieved a good result on the analysis. So, talking about the offline analysis, as I said before, one of the targets is the redefinition of the pass-fail criteria. In particular, what we have done is for each test, we analyze the overall data set. We define new threshold of acceptance, so new criteria, and then we reprocess all the data available with a new concept in order to detect and validate the idea. So as you can see from this plot on the right, here we have an example, a very simple test about one actuator. And this actuator is verified in the rack position after each actuation. So we verify that the rack position is between two values after each actuation. As you can see on the x-axis, you have this rack position. On the y-axis, you have the actuation event. And the color represents different kits. As you can see from the top, the old threshold was initially very, very wide. And this did not allow to have a good control on this process. So the idea was to redefine a new threshold, as you see on the bottom, in order to have it very, very smaller, in order to allow a good control on this process. And this was a very good result. Then the second target of the offline analysis was the anomaly detection. In fact, what we have done is the identification of some possible anomaly, and then we defined a criteria for this verification. So we checked if this behavior happened or not, and we reprocessed all the data available in order to check on the entire storage of the data. As you can see on this example here on the right, you have the correct profile of speed, and on the top you have in blue the mechanical speed and in orange the electric motor speed, and you can see that it's a very specific profile of speed. And as you can see on the left instead, sometimes happened that this profile was completely different. So at the beginning, the test bench was not able to detect this kind of anomaly. But thanks to my software, we were able to detect this anomaly, and the test bench was modified thanks to this. And this was a very good point for my software. So those kind of analysis were applied on all of the tests available. So as you can see from this slide, you can see that for most of them, we correctly reanalyzed them and refined them in a good way. But in few cases, we were not so comfortable to have control on them. So we didn't understand very well sometimes what happened on the test, and in particular in those two cases underlined. So we decided to apply what is called the artificial intelligence to try to understand a little bit more on those tests. In particular, of the artificial intelligence, we decided to apply what is called the association rule. The association rule is an unsupervised algorithm of machine learning that allows to analyze data and define correlation between events. So basically, you start from the events of the dataset that are synthesized in a matrix, a binary matrix that represents the entire dataset. You apply the association rule, and you obtain the correlation between all the events. In particular, you have, as a result, a two-column vector in which each row represents the events that are correlated together. So I would like to show you an example of this application. This test 05, is a test about our pressure chamber. As you can see on the left, here we have the pressure channel in time, and the different colors represent the repetitions of the test. As you can see from the profile, you achieve a certain level of pressure, and then you apply an actuation on the actuator that was previously described, and of course it causes a pressure drop. But unfortunately, this pressure drop has a huge variability, and this did not allow to have a reliable test. So we wanted to understand a little bit more on the reason of this strange behavior. So we applied what is called the association rule that I introduced before on the pressure drop, rack condition, and oil temperature in order to check if there were some correlation between the events. And we defined those important results, underlined in yellow. We understood that the pressure drop has a low entity every time that the condition of the rack was in a disengaged condition at the beginning. Vice versa, the pressure drop was high when the condition of the rack was in engaged condition. So this was a huge result because we started to understand a little bit more on the reason of this pressure drop. Moreover, we also added what is called HCU, that is hybrid control unit, condition to the association rule. So we analyzed another time all the data set with one more variable. And we understood another thing, so that is the final result of this analysis. And we understood that the engaged condition, that is the unwanted one that we have seen before, is extremely correlated to HCU error. So this connection allowed us to define that the high variability of the system, of the test, was correlated to the HCU error. Just simply adjusting this point and modifying a little bit the procedure of the test, as you can see from the bottom, we completely changed the results. So we reduced the average drop of pressure by 72%, and the standard deviation, that is the most important factor, by 86%. So thanks to this analysis, it was possible to understand the reason and to find a solution to our problem. And this test, the test 05, was now used for the analysis. So as conclusion, I started from the end of line. I performed a software in order to perform an offline analysis. And when offline analysis was not enough, the artificial intelligence helped in this way. And at the end, as a result, we arrived to have a robust end of line, and so to have a very good control on this entire procedure. And this was the main target of the work. So it was very good result. So this is everything from my point of view, and I'm open to any question. Thanks for the attention.
Thank you, Gabriele, for your presentation. As usual,
you're welcome.
Any question or curiosities from the Commission? Well, I have a curiosity, obviously. Machine learning or artificial intelligent algorithms are affected by the number of data and the quality of data that you use to realize the analysis. How much data did you need in order to have a good results, and what's your future perception about the use of such kind of techniques in the realization of offline testing and offline testing?
Yes, thank you for the question. Yes, this is true. In fact, at the beginning, the idea was to use another kind of algorithm, but it required really a lot of data, and we were not we didn't have so many data. So we tried to use something that did not require so much data. So this kind of algorithm, what is called, as I said before, sorry, take just a picture. Okay, this kind of association rule is allowed to work also with few data, because it works just with the events. So you find just simply the correlation between events. And this was the main reason why we decided to use this kind of algorithm. And the most complicated part was just to create this kind of matrix, because you needed to elaborate the data. And of course, as you said, the result was extremely dependent from the input data. So it was necessary to have a good control on the entire system. The good point of the artificial intelligence is even if you don't have too many data, you can give to it everything that you have without any kind of physical model, and you achieve a result. If the results are okay or not, it's a matter of you. You have to understand the data, because this is not a model that substitutes the analytical analysis, because the data were not enough. But it allows to understand a little bit more, that gives you the input to go more deep in one aspect with respect to another. So it's just some information that you have more. I don't know if I answered to your question well.
Yes, perfectly. Thank you so much.
You're welcome.
And so I ask to the next candidate to share the screen is Claudio Ragusa.
Good afternoon.
Good afternoon. I don't know if your supervisor was able to join us.
Yes.
Yes. Can you hear me?
Oh yes, perfectly. Hi.
Okay. So just to briefly introduce Claudio's work, he did an internship here in Dallara. The first part of it was done from home, let's say, in the end of the 2020, and then in the beginning of 2021, he came here to complete his work. He did a MATLAB application about the virtual poster rig, so-called. So it is used to help and integrate our real poster rig sessions. So it's about poster rig testing, and we needed a tool, a software tool, to help with the hardware one. He used a completely fresh approach and started from scratch. So what he was able to do in the time he had is quite impressive, in my opinion. He will continue to work here and try to get better and better with his software.
Thank you, Alberto. Good afternoon, everybody. I'm Claudio Ragusa, and I'm going to present you the virtual poster rig. The poster rig is a machine used to study the ride dynamics of road and racing cars. Ride is the branch of vertical dynamics in which the frequencies are between 0.25 and 25 Hz. And in road cars in particular, it is studied to improve comfort and enhance road holding, while in racing cars there are three main tasks. The first one is to keep the contact between wheel and ground as uniform as possible, and this is because of tire non-linearity with respect to the vertical load, and so we want to minimize the vertical load variations. The second one is to optimize the body position with respect to the ground, and this is because the racing cars have usually a high downforce, which varies a lot depending on the ride heights. So ride height variations can change both the total downforce and the aerodynamic balance. And the third one is to optimize the wheel position with respect to the ground, because we don't want this exaggerated camber of the right car in the top figure. Clearly, instead, comfort is a secondary target in racing cars, because the focus is on performance. The poster rig is at least made of 4 vertical actuators, which are called wheel pads, and they move vertically to represent the ground excitation. The car is land on these 4 actuators, and in this case we have a 4-post rig. There could also be 3 additional actuators, which are called aeroloaders, and they are attached to the chassis of the car and apply vertical loads to it to represent the aerodynamic downforce and the load transfers. In a 4-post test, is mainly modal analysis in which the 4 pads oscillate with increasing frequency and decreasing the oscillation amplitude, so that the amplitude of their velocity is kept constant, as you can see in the top left figure. And in this way we can scan the ride frequency range. In 7 posts instead, the main use is the track replay, where the 4 pads move according to the real, let's say, measured excitation of the road in a lap in the track, while the 3 aeroloaders give the downforce and the load transfers according to the measured ride heights and to time histories of the speed trace and longitudinal and lateral acceleration traces that are recorded during a lap in the track. Usually the analyzed outputs are the contact patch load, that is the vertical load exchanged between wheel and ground, that, as I said before, we want to minimize its variation. Some body control indexes, like for example tab pitch, because tab pitch can changes the ride heights, and so changes also car aerodynamic balance. And another one is the transfer function between strut load and strut stroke, which are the load measured by the push rod and the displacement of the damper. And the phase of this transfer function tells us how much is the damper contribute with respect to the spring one. Then we come to the virtual poster rig, which, as Alberto said before, is a software used to simulate poster rig analysis. And it has been developed keeping in mind two key concepts that are generality, because it can be used for any type of car with any suspension elements equipped, and modularity, because it is divided in many different modules, and the user can choose to use all of them or only some. The mathematical model lying behind this software is a 8 degrees of freedom 1, in which the degrees of freedom are the 4 unsprung masses vertical motions, namely hop, the sprung mass bounce motion, pitch rotation, and 2 roll rotations, because we are considering that the chassis is not infinitely rigid, but has some torsional flexibility, and so the roll angles can be different from front to rear. This mathematical model then has been transferred in a Simulink model, which you can see as a general overview, say here in this slide, and it is divided in many different subsystems, each one containing a group of equations. So we have the input subsystem, in which are defined the time histories of the wheel pads displacement and the rollers forces. Then we have the constitutive equations, unsprung and sprung masses equilibrium equations, the congruence equations, and the subsystem to calculate the ride heights. After this, I developed a graphic user interface in MATLAB App Designer, which is divided in many different tabs that correspond to the modules that we saw before when I talked about the modularity of the software. So in this slide, we can see the maneuver data tab, in which you can select among different maneuvers that are the single harmonic bounce, so where the 4 pads oscillate with a single frequency and simultaneously giving a heave excitation, the sine sweep, which is the modal analysis that I spoke about before, the warp test, it is the one that showed also Valerio Caliciotti a couple of hours before. So the 4 pads oscillate very slowly, giving a torsional excitation to the car. The curve strike, in which the car passes over a curb on one side, and the pull down, in which the 3 aeroloaders pull the car down. And then you can also load a custom maneuver by pressing the load maneuver data button, and so you can run any different maneuver. After this, you can save the maneuver in a math file and move on to the vehicle data tab. Here you can set the car geometric and mass parameters, as well as the chassis torsional stiffness, the static ride heights, and the downforce coefficients aeromass. And then we have the suspension data tab, which is divided in many different sections, each one for each suspension element. And this is because the car is equipped with any existing suspension elements to make it as general as possible. And so we have the springs, dampers, inerters, anti-roll bars, and third elements. And for each component, you can define the motion ratio curve and generate its force curve starting from the coefficients or loading it from a spreadsheet file. So, for example, here we can see the spring section, in which you can define the force curve by defining the linear stiffness and the maximum deflection of the spring. If there's a band stop presence, you can define its gap and the quadratic coefficient to represent its contribute. And then you can also set spring preload and insert suspension compliance, that is an additional spring in series to the main one. And as I said before, you can load the force curve from a spreadsheet file by pressing the button. Then we have the dampers tab, another example, in which you can define the damper curve starting from 4 damping coefficients that are low and high speed damping coefficients in bump and rebound and are set independently. And you can also set, of course, the transition between low and high speed behavior, also here independently from bump and rebound. And you can also set the suspension stiction, that is the static friction of the suspension, and it gives a step to the damper curve around the zero velocity position. And once again, you can see the load force curve button to load the force curve from an Excel file. Then we move to the tire data tab, in which you can select the tire model and its inflation pressure and see how the stiffness and damping curves change. And also here you can clearly load the force curves starting from a file. I also developed a setup tab, which in this case is not general but specific for a certain type of car. So in this slide, for example, you can see that it has been developed for an F2 car, and the concept of this tab is to keep all the tunable parameters in a single tab to make quick setup modifications. So as you can see, you have all the suspension parameters, tire pressure, camber angles, and so on. And after this, the setup is saved in a mat file, like we did before for the maneuver. And so you can load the maneuver files and the setup files and run the simulations, which are any possible combination of maneuver and setup, and are run in series. We have also done a post-processing tab to make you see some plots of the time histories of some relevant quantities, like the degrees of freedom and the ride heights. But more importantly, the simulation outputs are saved in an additional mat file, so that you can process them as you want. After this, we have done testing on a real car, that is a dummy F2 car, at the LR7 poster rig, and this has been done, of course, to validate the model. We have done pull-down warp, constant frequency eve, and modal lift test. The pull-down test has been done to check and correlate suspensions and tires' vertical stiffnesses. As you can see in the top left figure, we have done scatter plots of the 4 contact loads versus the 4 damper displacements reported at ground by multiplying them times the corresponding motion ratio. The slope of these scatter plots are the suspension vertical stiffness of each corner. And as you can see, the real data are the red ones, while simulation outputs are the black ones, and the slope is the same. Then the warp test has been done to correlate the roll stiffness, because in this case also the anti-roll bars take a roll. And here I reported the 4 time histories of the 4 contact loads. Also here the colors are red for the real data and black for the simulation outputs, and you can see that the time histories show the same shape. Instead, the eve maneuvers are no more quasi-static but are dynamic, so that we can understand the car dynamic response. So in this case, you can see, for example, in the top figure, the contact patch loads envelopes in a model test, and the color data are the real ones, while the black data are the virtual ones. And you can see that the shape is almost the same. Instead, in the bottom figure, I reported the transfer functions between tab and road accelerations, where the tab accelerations are measured by 2 accelerometers placed on the chassis in correspondence of the 2 axles. And you can see also that also the trend of this transfer function is the same. So in conclusion, we can say that the developed model has resulted to be a valid tool, because you can see that the results are similar from reality to the virtual ones. And it is also a versatile tool, because it can be used for any type of car, and its short simulation time allows us to perform many different simulations in a few minutes. So it could also be used at the track, where we have a short time to take decisions. As a future development, instead, we will improve friction modeling to have an even better accuracy of the results. Thank you for the attention.
Thank you so much. You have some time for a short question from the Commission. Okay, so your presentation was clear enough, so you're lucky today.
Thank you.
We can move to the next candidate. This is Pietro Tugnoli.
I'm here. Good afternoon.
Good afternoon. I see that your supervisor is present at the moment.
Yeah,
is this
yes,
correct?
I'm here. Yes.
So please, if you want to introduce the candidate.
Yes, you are going to see the project of Pietro. He worked on an introduction of the third element on a high performance car. It has to be said that our customer usually think that the third element is a very complicated and expensive feature for the car, but Pietro developed this system in a very, let's say, simple way and economical way. So we, thanks to his work, we would like to present to our customers this system and to introduce in an existing car.
Okay, thank you very much, Andrea, for the introduction. Yes. Okay, so again, good afternoon, everybody. The title of my thesis that I developed during my internship in Dallara is a study and design of a third element for a suspension of a high-performance Formula car. So let's start with an introduction about the Formula car suspension. In general, for any kind of vehicle, the suspension system has to ensure a uniform wheel-to-ground contact and a proper level of comfort for the occupants. If talking about a race car, in addition, the suspension also has to optimize the wheel position with respect to ground in order to exploit at best the tire potential, and also to optimize the body position with respect to ground, in this case for a matter of aerodynamic performance. The problem with that is that very often these requirements are in conflict, so that, for example, you would like to have a stiff suspension for the body position, while a softer suspension in order to make the contact patch load more uniform. So we need to find the best trade-off for the car setup. Besides that, when talking about suspension stiffness, we should distinguish between the vertical and the raw stiffness. The vertical stiffness is important in straight line condition at maximum speed and while braking, because it has influence over the ride height that is a key parameter for aerodynamics. The raw stiffness instead is important in cornering condition because it affects the different lateral weight transfer between the front and rear axle, and this translates in the understeering or oversteering tendency of the car. So now, since the vertical stiffness and raw stiffness are important in different driving conditions, the best thing that we should do is decouple these two kinds of stiffnesses. Now, let's look more in detail how this decoupling is in practice obtained. And let's look at the suspension, the front suspension of the Formula car that I analyzed. We can see in particular the corner spring, that in this case is a torsion bar, that contributes to both vertical and raw stiffness. There is then the anti-roll bar that contributes only to the raw stiffness. Then there is the third element that in the original version of this suspension is missing. That is another spring, also called heel spring, that has to be connected to the suspension system in a way that it works only in the parallel wheel travel condition, like for example in this picture. So with the introduction of third element, we can increase the level of decoupling in the suspension so that we can increase vertical stiffness without changing raw stiffness, or vice versa, to decrease the raw one without changing the vertical one. And this second aspect is the one important for my case study. In the preliminary phase of my job, I had to choose the third element layout. For the front suspension, where the two rockers lie in the same plane, as I showed in the previous slide, the third element is installed directly between the two rockers. At the rear suspension, instead,
the third element is attached one side to the anti-roll bar, while the other end is fixed to the chassis. I had then to define the target stiffness for the third element, and to do so, I analyzed some real data from the driving simulator, and in particular, I analyzed 3 laps in Monza, Barcelona, and Spa-Francorchamps. And I developed a model based on an Excel worksheet that tries to replay the vertical behavior of the car. In particular, I take in input ride heights in static condition, aero configuration, and speed. I can play with parameters such as corner spring type and bump stop type and gap on the corner dampers, while I have in output the damper travel and so the dynamic ride height. In this graph, we can see in particular the plot of the damper travel versus speed. In the background, the small dots represent the real data from the simulator, while the bigger dots represent the behavior of my model, both for the front and the rear axle. And we can see a good match between the 2 data sets. I used this model, finally, to identify the target stiffness for the third element. Running this model in different suspension conditions with varying the corner spring and the bump stop type and gap, with the target of replaying the same dynamic ride heights of the simulator in order to have the same vertical stiffness. In other words, the idea behind that is to introduce with the third element the vertical stiffness removed from the spring and from the bump stops. Now, from the results of the stiffness analysis, it starts the embodiment phase. And as a result, as expected, we have that the ultimate third element stiffness happens in the condition with the softest corner spring and without bump stops. We can also see, plotting the third element required stiffness with respect to speed, that it has an increasing behavior with the speed. Then I had to translate this target of stiffness at ground in terms of requirements and constraints at the element itself. And to do so, I had to perform a kinematic analysis of the suspension with the third element, and I obtained the value of stiffness of the element that I have to respect as target, and the third element travel. Now, considering these requirements and constraints, I had to design the elastic elements to use for the third element. The best kind of spring to use is represented by Belleville springs, because it is possible to combine them to form many stacks to tune the stiffness characteristic and reach the desired stiffness progressivity. So in this table, we can see in particular 3 examples of Belleville stacks that are realized combining a different number and different geometry of Bellevilles, and we have so different total height of the stack. At the rear third element, unfortunately, for some packaging issues, it was not possible to use Belleville springs as at the front, but I anyway selected 2 sets of helicoidal springs that can match with the target that I defined before. Now, looking at the detail of the third element design, you can see in this picture the final geometry of the element with that characteristic length. And in particular, I would like to show the preload adjustment system that is required in order to have the possibility to fit different kind of Belleville springs depending on the desired setup. This adjustment system is realized by a ferrule and a lock nut, and we have a useful range of 41 millimeters as shown in the picture. Now, to mount the third element in the suspension, I had to modify the existing rocker, and I had to add, of course, the third element attachment point, and to move by a few millimeters the push rod attachment point because of some clash issues. I had then to identify the dimensioning condition to verify the modified component, and I found out that the dimensioning condition is the jump over curve maneuver that generates at the third element a maximum load of 20,048 kilograms in the condition of parallel wheel jump. I used this value to perform a finite element analysis over my modified rocker, and you can see here in the right the result of the analysis. I also performed a FEM analysis over the original rocker in the original loading condition in order to get a baseline for the result comparison. We can see a similar level of stress, safety factor, and deformation, so the component is verified. Now just a brief overview about the rear third element that is available in two versions for the two different set of springs that I selected. And in this case, in the case of the rear suspension, I had to modify the existing anti-roll bar in order to add the third element attachment point in the middle, like in this detailed picture. And I also designed from scratches the clevis to fix the third element to the gearbox, which is the green tab in the picture. Now, going to the conclusions, we said at the beginning that the target for this of this job was to increase the level of the coupling in the suspension, and in particular to reduce the roll stiffness without changing the vertical one. From this plot, we can see a comparison of the roll stiffness in the original condition of the simulator in blue, while in orange there is the roll stiffness of the modified suspension with the introduction of third element that allows us to run with the softest kind of corner springs available. And this without changing the vertical stiffness as target. So under this point of view, target achieved. Then this goal is reached without big changes in the existing suspension, because we have that we should introduce only one new component, which is the modified rocker for the front suspension, and two components for the rear suspension, the attachment tab and the modified anti-roll bar. Also, the weight increase is very negligible compared to the suspension assembly, and even more if we compare it to the weight of the total car. So also under this point of view, we can say that the goal is achieved. So this was my last slide of this presentation. Thank you very much for your attention, and I'm available for questions if you have.
Thank you. Thank you so much for the presentation. Any questions? Well, you perform an optimization regarding three particular circuits, sharing some characteristics, obviously. Are you performing the same approach also to other tracks that have different characteristics? And so you are...
Yeah, the choice of the three circuits are was made in order to cover the widest possible range of circuits. We have a very high speed circuit with low downforce aerodynamic configuration, such as Monza, while Spa for medium configuration, and Barcelona for high downforce configuration for the aerodynamics. And I did this choice because with my approach, the very important parameter to consider was the ride height that is very affected by the aerodynamic.
Okay, thank you. So what was any future development for?
Yeah, for sure.
According to this,
my job was concluded with the design of the element, but for sure the element could be tested at first stage at the simulator to have a first feedback from the drivers, but then it could be possible also to have a characterization testing the element at the test bench, or also in a future moment also at the poster rig before a possible final testing track.
Thank you. Any other curiosity from the Commission? Okay, so thank you again. We can move to the next candidate. Kay and Yagmai, so welcome.
Yes, good evening to everyone.
I guess that you have the same supervisor introducing you?
Absolutely, yes.
So
yes,
please.
Correct. Yeah, Evan work on an hypothesis of pedal system. It has to be said that the Lara usually develop a dedicated pedal system for each car, even if every system is very similar to the other. So Kevin tried to develop a system that can be used in almost all the Lara racing car, so that we can shorten the design period and the cost of these components.
Yes, thank you, Andrea.
Yeah.
So, as Andrea said, my master thesis it's of a study of a universal pedal assembly design for a racing application. This thesis was entirely developed in Dallara with the help of Andrea and the entire design office. So let's start from the problem. From go-karts to F1, the main controls that a driver has of the vehicle are pedals and steering wheel, but these have not the same importance for a race car because the throttle and steering application are a direct consequence of the braking phase. So between these three main controls, the brake pedal is the most important to drive a race car, and the second one is the throttle. In a monomake series in which Dallara is a leader, cars are used by many different drivers that have different heights and are used also in different seasons. This means that one team buys a car, for example, a Dallara car, and it must be sure that without designing new parts, it can accommodate different drivers with different habits, and thus the necessity of developing systems that have a big range of adjustability in position and feedback. For
so
each new
use the presentation mode for the presentation. Now we are viewing the standard mode.
Yes, this is the. Wait a second. Let's try. Can you see the presentation now? Full screen?
No. Now yes. Okay.
Okay. Perfect. Sorry for that. Still full screen. Can you hear me?
Yes, please continue. Yes.
Perfect. Okay. Perfect. Sorry. So for each new car, Dallara spent time to design and adapting the pre-existing pedals to the new chassis, like Andrea Nicolazzi said. So with this project, the goal is to reduce this time to the minimum, at best eliminate it, and this time to adapt the entire pedal box to a new project. So the universality of the project is a core characteristic. So this thesis work has the goal to develop a pedal box that can be used in all the future Dallara racing cars as a plug-and-play assembly, more or less. A pedal assembly or pedal box is composed by these main components that you can see on the slide. And nowadays, clutch pedals are always more rare to find in race cars. Thus, in this thesis is considered as a secondary sub-assembly. As it can be observed, also the assembly is quite complex and has many different attachments point to the chassis. So the space for the mechanics to adjust and assemble and disassemble these components is quite limited. As you can see in the picture on the left, normally they can access to the system through the seat of the driver, which is quite small, and from not always from some openings at the top of the chassis and in front of the chassis when the front wing is detached. So the first part of the project focused on the conceptual phase, and as first a benchmarking was conducted between all the pedal assemblies developed and designed in Dallara in the last decade. Also commercial products were considered in formula, open wheel formula cars, closed wheel formula racing cars, and GT cars. They were used up to 17 parameters to evaluate these assemblies, and also the main technical rules of interest were studied and for each subassembly, a functional analysis was carried on with these inputs. For each component, a goal was set. This analysis was conducted using Excel spreadsheet. So the throttle pedal main goals are to reduce the volume, simplify assemble operation, and eliminate buckling. All three goals derived by the use of the throttle linear damper, which is positioned nearly horizontally to keep the motion ratio as constant as possible, like you can see on the picture on the left. This implies a bulky design. So to eliminate this extra volume, I chose to use a rotary damper instead in this project. The current design also needs two attachment points to the chassis, the pedal one and the support one, which have 4 screws. And in the new one, instead, there is only one support that has to be connected to the chassis, reducing the 4 screws to 2 screws. This is nearly halving the time needed by the mechanics to adjust, dismount the unit from the car, which is a lot of time considered, for example, in a race. For the rotary damper, I selected a commercial unit to substitute the current one, which is designed and built currently in Dallara, and it's a single effect damper. The damping coefficient of the linear damper were analyzed and compared with the commercial ones, and the maximum damping torque now it's higher of nearly 20 Newton per meter, which it's a very good thing because it increases the adjustability range. And the damping coefficient of the rotary unit is also continuously adjustable, which is not a feature available for the linear one, which is an important benefit in terms of adjustability. This layout, on the other hand, changed the whole force path in the components. In the current assembly, for example, the pin, which is the yellow one that you can see in the photograph, which connects the pedal to the potentiometer, only needs to transfer the rotation of the pedal to the sensor, while in the new configuration it must carry all the damping torque, and this forced a complete redesign of the components. The spring also changed from linear to torsional, which must have different stiffnesses that cover the actual linear spring range, which is quite extended. The brake subassembly main goals are creating a single support, eliminate buckling, and adjustable pedal ratio. The same buckling risk that we encountered in the throttle pedal assembly is present here in the brake assembly, where extensions are needed to adjust pedal position, as you can see in the photo on the right. And possible interference also with other suspension components can occur during motion. This single support that you can see in pink will give a solution for the buckling and simplifies the assembling operation for the mechanics. In this case, from 2 support, as you can see on the left, we pass to 1 support with only 3 screws, while on the current design we have 5 screws that are interfacing and interacting with the chassis. Another important feature of the new support, it has floating nuts which are riveted on the support, and this makes possible to one single mechanic to dismount the whole unit from outside the chassis. The third main goal was to have an adjustable pedal ratio. This choice has many reasons, like the difference of height, thus of feet length between the drivers, and this difference has a very big impact on the energy consumed in the braking phase during a race. With this shape connection design, it's possible to adapt the car to different driver's foot dimensions, changing the pedal ratio. This becomes even more useful when we consider that the women are finally participating more in motorsports, driving the same cars and usually have smaller feet. The forces on the brake pedal are quite high. Consider that a normal brake application during a race can be around 180 to 100 kilograms, and can reach over 200 kilograms in the case of adrenaline boost. The standard in Dallara is to dimension the pedal and all the brake pedal components at nearly 250 kilograms in static conditions. So the pedal with this load case was optimized from the simplest and lightest possible configuration that you can see in the left picture to the right one. And while the support that you can see on the bottom was dimensioned in two with two load cases. The first is the static normal operation condition, while the second one, it's a failure mode load case. This is the case in which one master cylinder fails and the other one must provide the possibility to the driver to stop the car safely, so it carries all the load and all the braking force. This load case is used to compare the already used support that you can see on the bottom left with the new one that you can see on the right. And the results demonstrate that both supports react in a similar way to this load case, which is very extreme. Considering the clutch subassembly, the one already used in the Lara satisfied all the goals of the functional analysis, so no redesign was necessary, and it has already a single support like the brake pedal and the throttle pedal, which makes it easy to assemble and disassemble on the chassis. We can have now overall comparison of costs. And for this comparison, the current reference is a Dallara Formula race car. For the throttle subassembly, we can see how shorter it is and also cheaper. This is mainly determined by the difference in cost of the damper. Consider that the rotary unit is nearly 30% cheaper than the Dallara one. And obviously, reducing the volume behind the pedal, we gain volume at the side of the pedal. So this brings the subassembly to be 24 millimeters wider. That it's the red data that you can see in the screen. For the brake subassembly, which is in the bottom part, we can immediately see a very big cost reduction, nearly 25%, mainly coming from the choice of using commercial rod ends and the simplification of the balance bar assembly. The weight increase is mainly due to the single support, which has obviously more material, but it's compared with the reference version of the Formula car that has no extension. So the weight increase of 133 grams is not to be considered as a negative result, because actually it must be considered also the fact that it's the new pedal has an adjustable pedal ratio. So to summarize, this is the complete pedal assembly with the 3 units, and universal design for each module, which is fast to assemble and adjust. It's achieved with also a considerable cost reduction. And as future developments, a driver sensitivity campaign must be done for sure to acquire some feedback on the new systems, like for example the rotary damper. And also on the rotary damper itself, a fatigue test should be performed. And then the whole assembly should be produced and tested in the simulator with different drivers to compare the data with the current versions. So thank you. That was the end of my presentation.
Thank you so much for the presentation. Very interesting. It's very difficult to optimize such kind of components that are well known and well developed, but from many companies. So it's a very challenging task to do that. So my question is, you had to consider many different requirements coming from different fields, electronics, more than hydraulics, more than mechanical background. Do you use any particular technique to arrange the different requirements, or was just a studying about the existing solution and a benchmarking regarding the existing solution?
It was a start as a benchmarking as the different solution with the 17 parameters that I cited before. And yeah, no special technique, meaning it's I followed the typical design procedure that we've seen during these 2 years of master degree also, and that was very helpful, and actually gave me the possibility to rethink, like you said, some functions of some components that are usually considered standard. I mean, they're never questioned their way of working. So with this you know, making a comparison with all the function of the components, it was possible to reinvent more or less some functions for components, like for example the rotary potentiometer, rotary damper.
Thank you so much.
You're welcome.
Any other question? No, thank you. So I call Federico Zuccari, who is the last candidate of the afternoon.
Good evening.
And Professor Sorrentino is going to introduce him.
Yes, good evening. Federico developed his final project within the driving simulator team in Maserati. And his main task was to explore the adaptability of the Passeca Magic Formula tire model to low adherence surfaces, and then to try to replicate the experimental behavior on the driving simulator. Okay, Federico, you can start your presentation.
Thank you for your introduction. I'm going to share. Okay, you should see my presentation now. Do you see my presentation?
Yes, perfectly.
Okay, so good evening, everyone. First of all, I have to introduce my thesis with a brief note. I have to remember that thesis is protected by an embargo, and so all the material presented here is to be considered as confidential. My activity was carried on at the Vehicle Dynamics department in Maserati, which is in charge of the virtual analysis and all the driving simulator activities. They have two different kinds of simulator. The one on the left, that is the dynamic one, and the one on the right, that is the static one. They both serve different purposes and are used for different purposes, as the left one, the dynamic one, is better to explore and to correlate the driver-car relationship, because all the feelings are better reproduced for the driver, while it has some weight constraints, and so some complex hardware-in-the-loop systems could not be implemented. On the other hand, the static one has no weight constraints, and so complex systems can be easily added to the cockpit. It's for this reason that the one that I used at the end of my activity was the static one, because I needed the hardware-in-the-loop to better correlate the electronic controls intervention. My objective was to create a virtual tire model to be used on the driving simulator that is capable of correctly reproduce the vehicle behavior on low adherence surfaces like ice and snow. In order to do so, it was used a Passeca Magic Formula model, which is a fully empirical model. This means that the formula is not related to the physics of the tire itself, but it's just a curve fitting a set of experimental data. There is another kind of very accurate tire models, which are the completely physical ones, which usually take advantage of the finite elements method. The Magic Formula tire model has the great advantage to have a low computational effort, and so it is suitable for real-time applications as the driving simulator one. This is the main reason for the model choice. Then, just to have an overview, before my activity, an extensive characterization campaign was performed on the physical tire on a scraped ice surface with the tire mounted on a skid trailer which output is a fitted tire model to be used as a baseline for my fine-tuning. After this first step, another experimental test campaign is performed with a full vehicle, and the data is acquired. And after this, the fitted tire model and the full vehicle experimental data are taken as input for my thesis activity, which consisted in properly scale the tire parameters in order to correlate the vehicle behavior with the experimental one. And after this first phase, there is the second one at the driving simulator, which is important to correlate the vehicle controls and to have a subjective evaluation from a skilled driver. Talking about the experimental tests, there are three main categories. The first one is the one with the tire alone, that is mounted on the skid trailer on a truck, like the one shown in the photo, which output is a complete magic formula tire model. The second phase is a test on the full vehicle with objective maneuvers performed to have an objective evaluation of the handling of the vehicle. These maneuvers are the slow ram steer, the frequency sign sweep steer, the straight line braking and acceleration, on which then the virtual model is correlated with the virtual simulations. In the slow ram steer, the car runs at constant speed, and a ram steer is applied slow enough to consider the maneuver as a quasi-static one. In the frequency sweep steer, the car runs at constant speed and a constant amplitude frequency sweeping steering wheel angle input is applied. In the straight line braking maneuver, with the car running at speed, the brake pedal is fully applied and the ABS system is in charge to modulate the corner pressures. While in the straight line acceleration, the car starts from standing still and a partial amount of throttle is applied with the traction control acting. There are here two types of traction controls, both acting together, one on the engine side and the other one on the brake side. The last phase instead consists in handling track runs in order to complete the assessment of the handling behavior also in combined conditions and to have the subjective feeling from the driver. The experimental data acquired on these tests on this type of surfaces present a much higher dispersion with respect to the usual high adherence one. So taking a slow ram steer maneuver as an example here in the graphs, the signals at different runs were synchronized with a trigger on the steering wheel angle, and then all the channels are averaged in time. With this operation, we passed from the blue data cloud on the red graph to the red one, which is far more readable and easier to correlate. Talking about the results in these objective maneuvers, a very good correlation is obtained with both the car real time and advanced car softwares, as is shown on the red graphs. On the upper side, we are looking at the elastic steering wheel angle with respect to the lateral acceleration in a slow ram steer. And on the lower side, we are looking at the transfer function for yaw rate over steering wheel angle over the frequency range. Here it is visualized the module. A very good correlation is also achieved on the straight line braking thanks to the hardware in the loop system on the driving simulator, while the straight line acceleration correlation should be still improved since the brake traction control model was to be optimized, and it is a physical factor, a critical factor on the first gears. After the correlation on the objective maneuvers, the virtual model is tested on the driving simulator and offline on real time on the handling track, both with a max performance event, so with a virtual driver on the virtual real time, and by a skilled driver on the driving simulator. On the left, it is reported the GG diagram for a single lap on real time, which is well correlated as it's visible, while on the right, it is reported the same graph for a lap on the driving simulator. It is visible how the longitudinal performance is overestimated in the track lap, but it was not possible to perform another session, so it is to be considered as a future improvement. Then, based on the driver's suggestion, a possible improvement is here presented, and it is about the snow blockage effect on the wheel side when the car encounters a massive oversteer. In fact, this effect helps to straighten back the car, avoiding a full spin. This kind of model should be modeled on Simulink and run in co-simulation with the driving simulator. The considered model to implement should take into account three main contributions. First of all, the tire slip angle, which quantifies the blockage effect on the snow. Second, the time spent on a certain tire slip angle, which takes into account the accumulation effect of snow. While the third one is the wheel rotational speed, which models the cleaning effect of the wheel under rotation, which acts as a moving wall for a fluid. To conclude, we can say that the results were overall very good and encouraging, and it's very important to say that the driver gave very, very good feedbacks about the car behavior, and so about the correlation with the real car. And the main improvements to do are the longitudinal friction coefficient scaling, as already said, and the implementation of the traction control model in the hardware-in-the-loop system to perfectly match also the acceleration maneuvers. Thanks for your attention. That was my last slide.
Thank you. Thank you for your presentation. Very clear and effective. So the last but not the least, as we are used to say, any comment or suggestion from the Commission? No, so thank you so much. And it's time for us to close this first part of the session. So I kindly ask to the members of the Commission to join me in the private room where we have the possibility to discuss and assess your thesis and your internships. And so you can wait for us here in the room, and we will be back in half of an hour. So I guess that we can respect the timing for the proclamation. Okay, so please to the members and also to the company supervisors, if interested on it, you can join me in the meeting that I'm going to create in the private room of Teams. So see you later.
c'era sito interrottivo.
Okay, good evening. May you hear me?
Yes.
Yes.
Thank you. I kindly ask to the member of the commission to switch on their camera if possible. And now we are going to call you one by one, and we are going to proclamate you with the final grade and the final evaluation from the commission. So the first one, I call Andrea Angione.
Here I am.
Thank you. Let me just open the file we prepared with all the assessments. So, Mr. Andrea Angione, the graduation committee took note of your course of study, evaluated your thesis work, and approved your graduation exam with a score of 110 on 110 cum laude. So, under the powers conferred upon this university rector and which are delegated to me, I declare and proclaim you a postgraduate engineer with the master degree in advanced automotive engineering. So congratulations from all the members of the commission.
Thank you to all of you.
So, Mr. Lorenzo Belletti.
Here I am.
The graduation committee took note of your course of study, evaluated your thesis work, and approved your graduation exam with a score of 110 on 110 cum laude. So, under the powers conferred upon this university rector and which are delegated to me, I declare and proclaim you a postgraduate engineer with a master's degree in advanced automotive engineering. So,
thank you.
Congratulations.
Thanks.
Mr. Valerio Caliciotti.
Here I am. Good evening.
Welcome. The graduation committee took note of your course of study, evaluated your thesis work, and approved your graduation exam with a score of 110 on 110 cum laude.
Thank you.
Therefore, under the powers conferred upon this university rector and which are delegated to me, I declare and proclaim you a postgraduate engineer with a master's degree in advanced automotive engineering. Congratulations.
Thank you very much.
Mr. Riccardo Calzoni.
Here I am.
Welcome. The graduation committee took note of your course of study, evaluated your thesis work, and approved your graduation exam with a score of 110 on 110 cum laude. Therefore, under the powers conferred upon this university rector and which are delegated to me, I declare and proclaim you a postgraduate engineer with a master's degree in advanced automotive engineering. Congratulations.
Thank you. Thank you.
Mr. Paolo Costi.
Yes.
The graduation committee took note of your course of study, evaluated your thesis work, and approved your graduation exam with a score of 110 on 110 cum laude.
Thank you.
Therefore, under the powers conferred upon this university rector and which are delegated to me, I declare and proclaim you a postgraduate engineer with a master's degree in advanced automotive engineering.
Thank you.
Congratulations. Simone Di Marco Bernardino.
Good evening.
The graduation committee took note of your course of study, evaluated your thesis work, and approved your graduation exam with a score of 110 on 110 cum laude.
Thank you.
Therefore, under the powers conferred upon this university rector and which are delegated to me, I declare and proclaim you a postgraduate engineer with a master's degree in advanced automotive engineering. Congratulations.
Thank you again.
Mr. Nicolò Ferrari.
Good evening.
Good evening. The graduation committee took note of your course of study, evaluated your thesis work, and approved your graduation exam with a score of 110 on 110. Therefore, under the powers conferred to this university rector and which are delegated to me, I declare and proclaim you a postgraduate engineer with a master's degree in advanced automotive engineering.
Thank you very much.
Congratulations. Alfonso Iezzi.
Here I am.
The graduation committee took note of your course of study, evaluated your thesis work, and approved your graduation exam with a score of 110 on 110 cum laude.
Thanks very much.
Therefore, under the powers conferred upon this university rector and which are delegated to me, I declare and proclaim you a postgraduate engineer with a master's degree in advanced automotive engineering.
Thanks. Thanks.
Francesco Marchianò.
Here I am.
Welcome.
Hello.
The graduation committee took note of your course of study and evaluated your thesis work and approved your graduation exam with a score of 110 on 110 cum laude.
Thanks very much.
Under the powers conferred upon this university, rector, and which are delegated to me, I declare and proclaim you a postgraduate engineer with a master's degree in advanced automotive engineering.
Thank you all.
Congratulations. Eleonora Mazzoni.
Here I am.
I cannot see you.
Now?
Okay. Here you are. So welcome.
Thank you.
The graduation committee took note of your course of study, evaluated your thesis work, and approved your graduation exam with a score of 101 on 110. Therefore, under the powers conferred upon this university rector and which are delegated to me, I declare and proclaim you a postgraduate engineer with a master's degree in advanced automotive engineering.
Thank you.
Congratulations.
Thank you.
Gabriele Pinelli.
Yeah, I'm here.
Here we are. The graduation committee took note of your course of study, evaluated your thesis work, and approved your graduation exam with a score of 110 on 110 cum laude.
Thank you. Thank you.
Under the powers conferred upon this university rector and which are delegated to me, I declare and proclaim you a postgraduate engineer with a master's degree in advanced automotive engineering.
Thanks a lot. Thanks to all.
Congratulations. Mr. Claudio Ragusa.
Good evening.
Good evening. The graduation committee took note of your course of study, evaluated your thesis work, and approved your graduation exam with a score of 110 on 110 cum laude.
Thank you.
Under the powers conferred upon this university rector and which are delegated to me, I declare and proclaim you a postgraduate engineer with a master's degree in advanced automotive engineering.
Thank you. Good evening.
Congratulations. Mr. Pietro Tugnoli.
I'm here.
Welcome. The graduation committee took note of your course of study, evaluated your thesis work, and approved your graduation exam with a score of 110 on 110 cum laude.
Thank you.
Under the powers conferred upon this university rector and which are delegated to me, I declare and proclaim you a postgraduate engineer with a master's degree in advanced automotive engineering.
Thank you. Thanks a lot.
Congratulations.
Good evening.
Mr. Keiyan Yamai.
Hello.
Welcome.
Thank you.
The graduation committee took note of your course of study, evaluated your thesis work, and approved your graduation exam with a score of 106 on 110. Therefore, under the powers conferred upon this university rector and which are delegated to me, I declare and proclaim you a postgraduate engineer with the master's degree in advanced automotive engineering.
Thank you very much.
Congratulations.
Thank you.
Mr. Federico Zuccari.
Here I am. Good evening.
Good evening. The graduation committee took note of your course of study, evaluated your thesis work, and approved your graduation exam with a score of 110 on 110. Therefore, under the powers conferred upon this university rector, and which are delegated to me, I declare and proclaim you a postgraduate engineer with the master's degree in advanced automotive engineering. So congratulations to you all. And before closing this long session of this afternoon, on behalf of the members of the commission, on behalf of the MUNER University and our department and our universities, I would like to share with you some general evaluation. I ask you to switch on your camera and to be part of this moment. It's a good look to see all you guys together in this moment. And switch off your microphone, please. But, well, just a few words to conclude this long day. You arrive at the end of a very difficult path, and you all arrive with a very high grade before the discussion of the thesis. That's the reason why we have so many final grade with the laude. And we discussed a lot to the commission because it's really impressive that so many of you arrive with the maximum of the grade. And sometimes it seems that we are too generous in giving you the marks. And we discussed a lot about that. And at the end, we conclude that you are very good students and you are very good engineers, and you deserve all the grades that we gave to you. So congratulations to you all for that. We know that you passed many difficulties along these 2 years. You had also the pandemic to help you in arriving at the end, and we understand that, and it's important that you finally arrive to this important goal and to this important target. And for us, it's important open the door for you to the job market, to the companies of MUNER, and we are proud of you guys, and we are proud that you have the possibility to stay into the automotive world. Well, another reason why you are here and you fulfill these important goals at the end maybe is the passion you have. You arrive from many different regions, you arrive from many different experiences during your bachelor, but you are joined in a common passion for automotive. And well, if we can give you just a suggestion for your future, is to maintain this passion. Maintain it every day, maintain it every year for your future career, because this is the real difference you have with other guys and with other experiences in engineering. Well, you are not alone. We know that you arrive at the end because you all have families, friends, supporters that helped you during these years, and so please tell they that they were important for you, and we are sure that they will be important also into the future. Is very important to remember all the people that helped you in the past, and so please tell them really thanks for that. So now it's time for having fun. It's time for prepare for the next future, because you know that today is the last day of the party. So the next time will be harder and harder. You are entering into a difficult world, and you are in the middle of a great revolution for automotive. So you have a lot of opportunities, but you have also a lot of challenges that you have to face. So congratulations again, guys. Thank you, and have a nice life and have a nice job from all the members of the commission and from MUNER as a whole. So good evening and bye-bye. See you soon.
Thank you. Thank you a lot.
Thank you.
Thank you. Thank you.
Thank you very much. Bye-bye.
Thanks a lot.
Enjoy the evening, enjoy the party, enjoy your life. Bye bye.
Celebrate, guys. Bye.
Ciao a tutti, grazie.
Ciao a tutti.
Ciao a tutti, ragazzi.
Ciao ragazzi, ciao a tutti.
Ciao a tutti, ciao ciao ciao.
Al lupo.
Che il divino Telma sia con voi.